Hey, hello everyone, and welcome to the Microsoft Research Summit, the Food Security Workshop. And this workshop is organized by Ranveer, Bash, me, and Riaz. And in this workshop, we are going to present the research and discuss the opportunities and challenges related to food security and R&D in food production. And uh, this 2 hour workshops will consist of diverse slate of speakers representing Microsoft research, academia, and industry. And today's session will focus on modern R&D, while the tomorrow session will work through the various elements of Farm Vibes AI. Okay, so before we start the talk of today, there is a few housekeeping notes. And the first one is this workshop is being recorded, and the recording will be made available for on-demand viewing 1 week after this event. And also during this workshop, please use the Q&A icon for the engagement with the speakers to allow for extended dialogue while keeping the session on time. And also, when you post a question, please note you have the option to post with your name or you want to hide your name. Okay. And so back to today's session, we will be focused on the challenges the food R&D industry faces in efficiently transforming data-driven insights and technology advances into food product R&D. So there will be a totally 9 talks as shown here, and all of those talks will focus on agriculture R&D related to genomics, computation, chemistry, and machine learning techniques and R&D functions. And we believe recent technology development can transform and modernize the R&D to enable agility, reduce cost, and deliver better outcomes. Okay. And yeah, so let's just start. So the first talk will be delivered by me. My name is Jiang. I'm currently a principal research manager in Microsoft Research Asia. And today I will talk about the recent AI advances for accelerant R&D in traditional industries. Okay. And we would like to first share our observations and thinkings based on Microsoft's research efforts of using AI research to empower broader industry domains. So in recent years, across our labs, we are working on a variety of hard problems across industries, from making carbon capture and storage more affordable to optimizing supply chain using a multi-agent system and to enabling a cloud-hosted financial exchange. And working on some of the problems which, if we can make a breakthrough option in the industry. And a challenge, though, is that such traditional industrial domains are not following a typical computer science discipline, and we don't have big enough research team to dig deeper into every industry. Instead, we decide to focus on 4 pillars that span all industries. They are including about connecting the last mile data, meaning the ability to get data from the remote sites. And the second is on data, which means we we hope to make sense of semi-structured data to enable data sharing. And the third one is on AI and the simulations. And nearly every industry we work with uses detailed simulations, and many of these simulations can be run faster and more efficiently using AI technologies. And finally, we are also working on how they can how our industry partners can meet their sustainability goals. And in the rest of this presentation, I will describe from what aspects we advance the AI development to empower R&D across industrial domains. Okay, so based on our engagement with various industry domains, such as supply chain, the CPG food, energy, finance, and sustainability, we observe that there are a few common tasks where AI or machine learning can play the key role, including forecasting, uh, the large-scale optimization, causal analysis and inference, as well as the simulation and backtesting. And so regarding each of these four pillars of common task, we have been advancing the development of AI technologies in recent years. Particularly, we develop a spatial temporal forecasting framework called FAST, which has been used in supply chain demand forecasting and medical forecasting in the health domain. And moreover, to pursue the finer grained forecasting, we also develop another very cool tool, the DeepMC approach that works better in weather and farming forecasting scenarios. And to address the large-scale optimization problems that are especially common in supply chain optimization, we propose a multi-agent reinforcement learning framework called MARO with the integration of deep and offline reinforcement learning algorithms to address the challenges learning from pure offline data. And we will talk about that later. And furthermore, many industry scenarios require a causal analysis and inference, which can be well addressed by a few MSR projects like DoY and Econ ML. Last but not least, regarding the simulation and backtesting, sometimes such things is very key to learn intelligent solutions for industrial scenarios. And we have some practice before, like we built QLib, which is financial investment learning framework, and it can empower you to learn financial modeling and to do a fast simulation and backtesting. And some other MSR researchers are also working on build a fast carbon storage simulation. And next, I will elaborate more about DeepMC, Maro, and our causal analysis tools. So regarding the first pillar about the forecasting, in many applications such as the micro climate forecasting in agriculture, we usually face the challenges of noisy, irregular, or missing data, or you you have to extract the rich spatial and temporal patterns, and you may also face the data with a complex signal with multiple granularities. And so to address these challenges, we have conducted extensive research on deep learning-based forecasting with data-driven imputation, alignment, and normalization, and a hybrid neural network structure to capture the rich spatial and temporal patterns, as well as multi-scale learning to capture those complex multi-granularity signals. And so combining all of these ideas together, the MSR researchers proposed a deep learning framework called DeepMC. And so apart from those three considerations, it combines the local sensor data with a weather forecast from the nearest commercial weather stations providers to generate the accurate microclimate predictions. And for this work, the local sensor data is collected using a FarmBiz, which is a commercial IoT platform for data-driven agriculture, which provides consistent data collection from various sensor type with a varying bandwidth constraint. And this is a system which is deployed for various applications in agriculture and energy. Yeah. And actually, DeepMC have been applied into more scenarios like the wind forecasting and the micro radiation prediction, and we also find that in each of these two, like CNN or LSTM and other traditional forecasting method. Okay. So the second pillar we just mentioned is the large-scale optimization, which is widely is very popular scenarios in the supply chain optimization. And so in many optimization applications, uh, like the resource rebalancing, inventory management, and order fulfillment, they all face the challenges of delayed feedbacks and even multiple optimization objectives. And there will be a huge computational cost for learning the optimization through the online interaction. And furthermore, the industrial problems usually have a very high state dimension and huge action space. So in such case, making the global optimization is highly difficult. So to address these challenges, we have conducted extensive research on reinforcement learning in terms of the reward shaping, the continual offline reinforcement learning, as well as distributed multi-agent reinforcement learning. And so so based on that, we develop a multi-agent optimization framework called Marrow. And beyond the typical offline reinforcement learning, which learns the policy only based on only the offline collect data. This continual offline reinforcement learning means that we have the chance to deploy the updated policy into online environment for multiple times, and its interaction with the environment will be logged for a future policy optimization. And when we talk to our customers, we also find that most of the current reinforcement learning system cannot afford the training with a great number of agents, such as thousands of ports in ocean transportation or millions of SKU in the retailing networks. And to address this problem, we also build a distributed framework, which consists of uh, uh, delicate algorithms and architecture design to ensure the efficient management of a massive offline experience data and high learning efficiency for a great number of agents, balanced training workload in the distributed system, as well as into various scenarios in the supply chain, and especially the resource repositioning, inventory management, and the routing problems. And in each of these scenarios, we have observed that using our multi-agent reinforcement learning based method can achieve better optimization results, and more importantly, a very efficient decision making in the when you use this multi-agent reinforcement learning approach compared to your traditional combinatorial optimization approach. Okay, so last but not least, we would like to introduce our recent advances on causal analysis and inference. So the essential objective of causal analysis and inference is to answer the what if question. So in industrial world, we need to answer it from observational data at a large scale. And in contrast to existing approaches, causal analysis and inference in practice faces challenges in terms of the cost, the scale, and the real-time issue, as well as the resolution of your scale. So because most of existing approach are not scalable to many engagement programs, and there could be you may need to wait a long time to get the causal analysis or inference results. So to address those challenges, the MSR researchers have provided new technologies to address these issues. So actually, we have a research team which is the first to bridge the causal discovery, causal inference, and deep learning to enable a scalable, flexible, and real-world end-to-end causal inference framework. And with our MSR technologies, the users can only provide existing data, and the tools can help them to discover the causal relationship and estimate the impact of your actions. And so answering these what-if questions and providing an optimal decision recommendation will be much easier by using our MSR-provided tools. So if you want to get more details, you may check the DoY library or EconML library, which has been released in GitHub. Okay, yeah, so a quick wrap up. So we just talk about how Microsoft research to advance the AI technologies in the abroad industrial world. And we talk about how we build up advanced forecasting and large-scale optimization, as well as causal analysis and inference technologies to empower our customers from different domains to enhance their R&D capabilities. Okay, so yeah, I think that's all my part. And so next, I will hand over to Satya, who is from the Microsoft Research India, and he will talk about the very fantastic work about the privacy preserving and model evaluations. Thank you.
Okay, I'm going to talk about confidential clean rooms for compliant AI. Sorry, am I audible?
Yes, we can hear you.
Yeah, okay, all right. Yeah. So let's consider a scenario where you have some private data, such as genomic data or soil data that you want to keep confidential, while also having a machine learning model infer on that data. And you want to make this data available only to that model and not to the service that provides this model, and not even the host that hosts this model in that service. And the way we can do that is to use encryption to provide this data only to the model using what we are defined, what I'll explain later in called confidential clean rooms. So the data is accessible only in a trusted execution environment. And moreover, the model runs in this trusted execution environment, which is sandboxed. What that means is that during the inference, the intermediate results of the data computation will also not be leaked to the external world. Sandboxing guarantees that the only means of communication between the model, the code of the model, and the external world will be through well-defined channels of communication, such as for the ingress and egress. And these ingress and egress channels will also be monitored for policy adherence, so that only policy compliant data goes into the clean room or the trusted execution environment, and only policy compliant results will be produced either to the client or to downstream services. And finally, all of these privacy and confidentiality guarantees can be attested by a remote service, for example, by the client, and before the data is shared. Okay, and because of the trusted execution environment's guarantees, the IP of the model is also protected. For example, if we have a scenario where we want to evaluate multiple models on multiple data sets, both the IP of the models as well as the privacy of the data can be protected using this framework. So I want to explain a little bit more detail on how we do this. Basically, confidential clean rooms is a core security component that we have built to develop trustworthy data processing services. And the main underlying technology is hardware isolated virtual machines, such as those using processors from AMD, 7 processors from AMD. We want to think about these services as composed of multiple microservices, and each of these microservices is hosted inside a pod or a container group. And that pod or the container group is what we are calling confidential clean rooms. And in each of these confidential clean rooms, we have a core business logic, which is the running the microservice, for example, the Onyx code of an ML model. And we don't want to trust this model or trust this code, the business logic. And that's the reason why we sandbox it. But at the same time, we um, support this business logic container with a large number of trusted sidecar containers, which provide the core infrastructure that we build. We being, the people who build the confidential clean room services. So you want to think about the client as a data provider and the business logic as a model provider. And this is the confidential clean room is the cloud infrastructure that we provide to enable, for example, privacy preserving inference or confidentiality preserving model evaluation and so on. Okay, so these these trusted sidecars do the attestation that I hinted to last time, and also the communication between the business logic and the external world is intercepted by proxies such as Envoy, and and that proxy does the cryptographic encryption decryption services as well as enforcement of policies on the data that is coming into and out of the confidential clean room. And on Azure, we use ACI, Azure Container Instances, that add the confidentiality guarantees using either Intel SPR or AMD processors that I mentioned before. And in addition to these container infrastructure on Azure, we have a pretty robust and versatile attestation infrastructure called Microsoft Azure Attestation, MAA, which can be used to provide the verification of the guarantees of the trusted hardware as well as the sidecar containers that I described on the last slide. Okay. Now, so far I've described how an individual confidential clean room works, and that corresponds to a microservice, but then we need to compose these microservices together to build a general service. And for that, we want to make sure that confidential clean rooms only are able to talk to other trusted microservices or or an external entity that is verifiably trusted, right? So for that, we designed an augmentation to the standard TLS protocol called mutually attested TLS. And here, on top of regular TLS, we also enable two CCRs, for example, to exchange attestation material so that one of this the peers can verify the trustworthiness of the other peer using the signatures generated from hardware and the code that is open sourced for policy checking and proxies and so on. Okay, so all of that can be verified, and only if the attestation is trustworthy will the data be encrypted to the other service, other CCR, and the communication, the subsequent communication proceeds. Okay, so using mutually attested TLS, you can compose CCRs together to build a large-scale distributed service in the cloud. So just to conclude, what do we have? We have these privacy and policy compliance guarantees, as I described before, because data is decrypted only inside the confidential clean room, and attestation and proxies and policy checks and sandboxing that prevents any exfiltration of intermediate values. But the reason why confidential clean rooms have been getting quite a bit of traction with a lot of customers that we have been talking to is that the business logic IP is protected, and it is essentially a lift and shift service in the sense that we do not even audit the code that is developed by the service provider. And that's why we actually call it untrusted business logic. And the service provider, or the business logic provider, could actually update them without the infrastructure being modified, without the infrastructure needing to be modified. And composability and using standard cloud native computing modules such as Envoy and Rego for policy checks and so on make this very easy to use by the developer ecosystem and easy to adopt with existing pipelines. So the goal for this project is to build end-to-end compliance framework, especially in machine learning scenarios. I just described for inference, but we want to do this for every step of an ML pipeline, including data collection, ingestion, curation, training, and deployment. And all of this uh, should be in a privacy preserving environment, and the guarantees provided by this privacy preserving environment should be verifiable. And that's very important because a certification authority or a regulator would want these guarantees and issue certificates that can be verified by third parties before they start using these services. Where are we now? We have been collaborating with an organization in India called iSpirit, which is kind of a policy think tank that is defining new models of sharing data, especially something called DEPA, Data Empowerment and Protection Architecture. And this model of data sharing is currently being applied in the scenario, financial services scenario. And one application in that scenario is lending. Here, the core objective in DEPA is data should be shared only with the consent of the end user. Like, for example, if you are applying for a loan, your data should only be accessible to a loan provider with your consent, and the consent could specify various user preferred policies, like how long the data is available and for what purposes the data uh, processed, and so on. So all of these could be captured in a digital artifact called consent, and that consent is what we enforce throughout the pipeline using the policy checks that I described in the confidential clean rooms. And we have a reference implementation that is currently being piloted with several stakeholders in the financial ecosystem in India. And we would love to try a similar implementations with the food security researchers here. Like I said, this is a scenario where we are applying. There is a small pipeline of statement analysis, like account statement analysis account statement that you would provide in order to process loan, and then there is a feature extractor, and then there is an inference, and each of them runs in their own confidential clean rooms, and more importantly, each of them could be provided by a different organization. And therefore they could be independently modified and independently evaluated. And we want to provide a service that remains privacy preserving despite these changes. There's still a large number of challenges that we need to solve. And one of them is that currently we only do very minimal policy checks that can be syntactically verified, but then a malicious business logic container could leak information through syntactically legitimate outputs, for example. And here we need something like differential privacy, and verifying guarantees such as differential privacy is not something that we can do within this framework right now. And we would like to go next into verifying algorithmic privacy guarantees such as differential privacy, and then use them as part of attestation. And a large ecosystem component that we still need to build is the certification and attestation. Like I said, a regulator would want to verify the privacy guarantees that are provided by a confidential clean room service, and then issue a certificate which can be validated by users of that service before they start using it. And for that, we need, just like we have PKI, public key infrastructure, we need an infrastructure for certifying confidential clean rooms. And that's something that we are working on in India. And this is something that we would need in order for confidential clean rooms to be usable on large scale applications in the world. That's the end of my talk, and I'm happy to answer any questions.
Awesome. So you should all be seeing my screen. My name is Sara Malvar. I am a senior researcher here at Microsoft Research. Today I'm going to talk a little bit about the combination of proteins and food, and how can we develop machine learning models to kind of approximate the protein digestibility. So we know that the world actually has a food problem. In 2021, the hunger affected almost 300 million people in Africa, 400 million people in Asia, almost 60 million people in Latin America and Caribbean. And we know that the prevalence of anemia among women is increasing, the adult obesity nearly double in the previous years. So, you know, malnutrition is a problem that we are facing. And again, when I say that the world has a food problem, I'm not really talking only about the amount and production, but again, I'm really focusing on nutrition. So we need to grow 50% more to feed the 2 billion people in the planet that we will have, mainly because 2 billion people lack vital nutrients. So more than 500 million people get sick by eating unsafe food. Agriculture and food waste has a huge environmental impact and footprint. So the key challenge here is that we need to increase production and decrease the environmental impact of the food that we produce. As I mentioned, the usage of sustainable food production, which incorporate the process of non-polluting, conserve natural resources, and are economically efficient, is imperative. And it's estimated that 25% of total global greenhouse gas emissions are directly caused by crop and animal production and forestry. In addition to that, humans eat a lot of animal protein, and by 2030, the poultry consumption will increase 120%. So that's a problem. If we want to eat good protein sources and we cannot increase our consumption of animal protein, we basically have a huge challenge ahead. Being a good technologist or a food scientist is not being a chef, right? So they basically use physics, chemistry to develop new food products. There are many aspects related to developing new foods, such as texture, for instance, how much a specific food stretches, blisters, and so on. There are also the microbiologists, so they take a look at the flavor, which is extremely important. The taste is directly associated to the molecular components of food. And finally, that's what there's the bioavailability context. So especially when we are dealing with plant-based protein sources, this is extremely important. So during a long period of time, people thought that plant protein sources were not as good as animal-based products. As a matter of fact, it's kind of a lack of perspective here. Mainly because to determine the protein quality, there are a few aspects that we need to observe. One of them being the biological value, which is correlated with our ability to digest this specific protein. And also the other one, which is the most important factor, which is the amino acid profile of this protein source. So a food source with a good amino acid profile, we have a good variety of amino acids and a sufficient amount of amino acids. Proteins, and let's get started by, the ultimate beginning, are very large, complex molecules that they play a critical role in the body. So they do most of the work in cells. They are required for the structure, function, regulation of the body tissues, the organs, and so on. The proteins there are made of hundreds and of thousands of smaller units that we call amino acids, and they tend to attach to each other in long chains. So the proteins are very similar to polymeric chains. The amino acids, they are basically organic compounds composed of elements like carbon, hydrogen, nitrogen, and so on. And the digestion process is basically the process of hydrolyzation of those components by enzymes in the stomach. So these long chains, they're broken down into what we call polypeptide chains, and then they're further broken into the amino acids. So those amino acids, they are absorbed by what we call some small parts in the intestines called ileum, and that's how we absorb the majority of the protein that we consume. In the human body, there are 20 amino acids that actually work as kind of the building blocks of the proteins. 9 of those amino acids are what we call the essential amino acids, and they must be consumed in the diet. There's no way that we can obtain that from other sources. 5 of them are considered non-essential, so they can be made by the human body. And there are also 6 protein-building amino acids that are conditional, so they can be or can't depending on some life stages, right? And why amino acids and proteins are important. So the thing is that amino acids, they build muscle, they cause chemical reactions in the body, they transport nutrients, prevent illnesses, and so on. So for instance, one of them is called histidine, and it facilitates the growth, the creation of blood cells, and so on. So, they are extremely important in all functional aspects of our body. Currently, there are basically 2 ways to measure protein digestibility in vivo. So if you are a food scientist and you want to develop a new food, let's say a plant-based protein, then you basically have 2 steps. You either use the feces of animals, and that could be either rats or pigs, and then you use something called PDCAS. And the other path that you can follow is using the amount of proteins that is absorbed in this small part of the intestine called ileum. And then you're going to use another protocol called DIAS. There are also some in vitro methods, but none of them actually correlate very well. So people tend to use those 2 in vivo methods. So the problem is that evaluating protein digestibility becomes extremely time consuming, it's lengthy, so it's also a costly process. So as I mentioned, one of these processes is the PDCAS, which is stands for Protein Digestibility Corrected Amino Acid Score. It's one of the most famous methods for evaluating the quality of protein, right? And the thing is that it is basically assessed by, as I mentioned, the feces of animals. The problem is that they identified that just checking the feces of animals was not very a good idea, mainly because the majority of the absorption was not happening in this stage, in the column, and so on. So in recent years, less than 10 years ago, they developed a new process, the DIAS, and they noticed that ileo rather than fecal digestibility is the critical biologically relevant parameter for amino acid or protein digestibility, mainly because the amino acids that appear in the column are most probably lost for body protein synthesis. So they are not being used or absorbed by our body. So this is why a few years ago they developed the DIAS. And the DIAS is this new method that computes the values absorbed in the ileum, so the small part of the intestine. Generally speaking, the protein quality within DIAS will range within a few bands. So any score below 75% in this scale will typically have no quality claim. So that means that it's probably not a good protein source. A good range of protein quality standpoint would be something between 75 and 99%, while any score above 100% is excellent or high protein quality, right? What is the problem here? Even though DIAS is, the best way to measure in vivo protein digestibility, the DIAS must be calculated using the ileum protein digestibility, and thus the material from the ileum must be used. So you can see that in order to do that, we basically need to use extensive animal testing using pigs. And the problem with that is that one needs to use sometimes more than 5 animals, and it can take 3 to 4 days of testing per pig for each food, plus the reference food that you're going to use. So it becomes a very long and costly process. So the question is there a way to accelerate the calculation of protein digestibility? Our idea is basically very similar to what we call QSAR, the quantitative structure activity relationship. So those are mathematical models that seek to predict kind of complicated physical, chemical, and biological properties of chemicals from those simpler experimental or calculated properties, right? So the QSAR methodologies, they have very good potential of decreasing substantially the time and the effort required for discovering new medicines, for instance, and they are actually pretty common to be used in drug discovery or, trying to understand the structural properties of one molecule and so on. So our idea was to kind of use a modified version of QSAR to predict the protein digestibility. So our first step is to create a data set that could be used to train our model. To our knowledge at this point, a ground truth data set for this kind of data did not exist. So instead, we have digestibility data in various papers and publications for a few raw foods. So in order to create the data set, we basically used 32 references for almost 200 food items. Just to obtain, the ground truth, which would be the protein digestibility, the DIAS value. Then we also obtained the protein sequence, and we use the fastest sequences, which are basically scientific data format that is used to store nucleic acid sequences or protein sequences. Then we obtain, for the most present families, at least 2 families for each one of those 200 food items, the fastest sequences, and we extracted biochemical information using some mathematical packages and also a language model. Then we also obtained some nutritional information such as dietary fiber content, sodium, zinc, fat, and others that we obtained from USDA, mainly because we know that some nutrients and anti-nutrients can very much modify the amount of protein that we can digest. So the baseline models that we train a whole bunch of them, and we observed that the tree-based classical models look the most promising at predicting the ileal digestibility coefficients of food. So we used these preliminary models, we analyzed the feature importance for our created data set, and we would also like to understand how the different features actually affected the model. So we used CHAP analysis to do that. And the idea here with this B-swarm plot is that each dot will correspond to an individual food and amino acid in the study. So we were actually able to obtain some of the correlations that are actually known in the literature. So for instance, some studies have shown that true protein digestibility in rats was negatively correlated with the total food fiber level. At the same time, the type of limiting amino acid is directly associated with the true allele digestibility, and some salts like magnesium and manganese are also associated with a lower rate of protein digestibility, mainly because they disrupt the enzymatic process. So we were able, with this set of features, to kind of extract some known relationships in the literature. Lastly, we wanted to integrate another feature extraction process. So we used a pre-trained transformer model. The idea was that a protein language model is kind of a model that uses the same concept as the language models from NLP. But the idea is that the tokens, in this case, are going to be the amino acids from the protein sequences. And then we are going to treat the entire protein like a sequence of the language model. So we use ProtTrans with, this is a 3 billion parameter model that has an encoder-decoder architecture. So we extracted 1,024 embeddings for each protein sequence. Remember that we had 3 families. And then we were able to add those new embeddings into the data set. So this large model, it was trained on data from protein databases such as UniRef that contains, over 300 billion amino acids compounds. So this is the final architecture of the proposed method. So for each food item, we have the nutritional information, amino acid composition, protein sequence of at least 2 foods, 2 families that are required. So the algorithm has 2 feature extraction steps. You have the biochemical information, which is extracted from the mathematical packages like protlearn, and we have the embeddings that are extracted from the language model. We have the baseline regressors that are trained in 2 feature selection approaches. We compare SHAP and the normal feature importance from ag-GBM. And then the true allele digestibility for each indispensable amino acid and food item is predicted, and the final DIAS value is calculated for 3 different categories: the infants, the children, and adults. So we ultimately train an LGBM regressor in the data set, and our model had an R-square of over 90%. We also conducted an ablation study, so we, had a whole bunch of different R-squares over the time, comparing model A, B, C, D, and E, while we, kind of deal with the combination of adding those features of the protein language model, adding the features of protlearn, adding the features, all the features, the feature selections using SHAP, and so on. And the best model, as I mentioned, was defined as the one using the selected features from SHAP values with the embeddings from the protein model. So as I mentioned previously, the model has obtained an R-square of 0.9. We also perform a sensitivity analysis. The sensitivity of each input is basically represented by a numeric value. In this case, it could be like the sensitivity index and so on. And it's pretty clear that the ProtTrans, or the embeddings that we extracted from the protein language model, they're responsible for over 50% of the variance, followed by the nutritional information and the categorical features, which are related to the protein families that we use, such as albumins, caseins, and so on. So I'd like to showcase the video of the tool that we developed. So this is the tool that calculates the food protein digestibility prediction. So the first thing that we have to do is to upload a CSV file with the nutritional information of the food item. So let's suppose that I am a food scientist and I want to develop something with almonds, for instance. So I uploaded a file with nutritional information of almonds, such as dietary fiber, energy, amino acid score, and so on. After that, we need to add the FASTA sequences of at least 2 different protein families. So here I added one for legumin, one for globulin, and I added I didn't have a third one, so I leave it blank. Then I selected the food group. in this case, because I was working with almonds, I selected legumes and oil seeds, and then I generated the predictions. So on the left-hand side, I will have the DIAS value. For children, the DIAS value for infants and for adults. Just for reference, the DIAS for milk is above 100. So almonds is definitely not the best protein source, right? And I also have this radar plot of the ileal digestibility of each amino acid score. So those are actually the values that we are predicting. We use these values to calculate the DIAS based on a reference value. So this result mean, for instance, as a food scientist designing a product with almonds, that I would have to fortify the product in some way because of the DIAS value, or the person would have to consume this product with another protein source to have a complete protein map. Here I have some other values for maize, tofu, and pork, raw value in this case. So we can see that we obtain very similar results from our model. Those are the ground truth obtained from experiments, and those are the predicted values. So one avenue for future research is basically to add some other features. We know that heat treatments, for instance, could alter the amino acid digestibility or the bioavailability levels. We know that the size of the food particles also impact the ileal digestibility. So the decrease in the particle size can increase the apparent ileal digestibility of pigs. So, you know, all those things, they might introduce some variance in the model and might be interesting to add those features and also other nutrient and anti-nutrient aspects. But overall, our model, you know, it's a very purely computational, ethical, and affordable model that can enable scientists to reduce the size of their experimental food matrices during protein digestibility experiments, especially when we are developing new foods, which is definitely something that we will have to do in the near future. Thank you very much. You can also read our paper, which is uploaded on arXiv. And right now, you will listen to the talk of Ronit Mandal from PPIC. Thank you.
Okay, so hello everyone. I'm Ronit, and I'm a postdoctoral associate at Plant Protein Innovation Center, or PPIC, in the University of Minnesota. So I'm basically a food scientist, and I will be talking today on applications of AI and ML in food process engineering. As Sara already discussed about the food security concerns, it's a major problem nowadays. And we know that there are 7.6 billion people and the population is increasing, and it will increase by 1.1% every year based on the statistics given by United Nations. And with this increase in population, there is also increase in the consumption as well as the spending ability of the food products. So the spending on processed food products has increased, and it will increase the double amount of the population increase, which means we need to process more food and provide more food or safe food for everyone in the planet. And that's where food processing comes into picture. Now, what is food processing? It is basically the transformation of raw materials into edible forms with one or the other technologies that I have mentioned in this slide. But mostly it is about conversion of the non-uniform raw materials into a uniform or homogeneous matrix. So there are many food characteristics like weight, size, color, shape, or flavors, and we can use AI or ML to kind of automate and process control in the food industry. It will help us in enhancing the economic value, minimize labor-intensive operations, reduce food wastage, and produce high quality and uniformity in the industry, as well as meet the growing demand, and also help in optimization. Now, when we talk about food processing, we need to know that food quality, food safety, and shelf life are a function of the temperature, time, relative humidity, moisture content, pH, and various other factors. And due to poor processing, there is considerable loss in food quality, and there is a food wastage, which is uh, a very daunting figure. Around 1.3 million tons of food is lost. So it is not only an environmental concern, but also it relates to the food scarcity, which is not needed, or which is a problem. Now, food manufacturing is a complex process, and it involves many factors like product flow rate, viscosity, temperature, concentration, moisture content, aroma, flavor, texture, and so on. Food is non-homogeneous, and the food processing itself is a non-linear function. There are so much interaction within those variables during food processing. Now, when we heat the food, there are many biochemical changes, and the moisture content also decreases if we heat the food or dry the food, which affect the flavor or texture of the food. The food properties like density, thermal conductivity, specific heat, viscosity, and so on, they are a function of the composition, temperature, moisture content, and they all vary during the food processing. Also, products are not uniformly shaped, or let's say they are not regular shape. They may be differently shaped. Let's say, for example, a broccoli, it is not uniform. So there's so much interaction and so much variation, non-linearity in food processing operation, and our brain is too small to capture all those details. So definitely we need machine learning and AI in food process engineering. Now, there are several roles of AI and ML in food industry, but mostly I will be discussing, or I'll be narrowing down the points related to the food security and food quality. So for food security purposes, it helps in food recognition and image processing, also helps in fertilizer management, in inspection and grading, robotics, or smart technologies. In terms of food quality, it helps in improving food quality uh, by use of AI. It helps in predictive modeling and helps in increasing the productivity and pesticide management. There are many operations in food processing, and we can use some of the ML techniques like machine vision, artificial neural network, genetic algorithm, fuzzy logic, decision tree, support vector machines. Uh, for time constraint, I'll be talking about first four only in my presentation. So uh, machine vision, as it sounds, it is a use of computer technology or computer vision to capture the details of the product and then quantify or tell us something meaningful about the product. So it can use cameras to capture, observe, evaluate, and recognize different objects. And it gets the image using different techniques like hyperspectral imaging, thermal imaging, and so on. And then it processes these images to give us meaningful information. And it can be used for non-destructive testing, like grading of food products, packaging quality checking, quality control, foreign object detection in food products. Let's say a package of chips. So basically, the product is moved under a camera, and its image is captured, and that image is processed, and that meaningful consider some eggs which are passed through a roller, and this image is captured, and that image can be processed further to tell us important features like if the eggs are clean or dirty, and if they have any cracks on their surface, which can help ultimately in the detection of cracks in egg or detection of dirt in eggs, and then it can help us better grade DX, because it is a very daunting task or very difficult task for its individual to perform it itself. So it saves time, and it is also non-destructive, which is very beneficial in the food industry. Secondly, grading of mango by size and maturity. Now there are some mango varieties which do not change color when they mature, which means when they get ripe, their color is still the same. So we can get their thermal image and then process them using machine vision technology to get meaningful information, like if the mangoes are ripe. Also, we can process their image and get information about their size, so that we can classify them into different grades of mango based on their size and their maturity. Next, I will talk about the use of artificial neural networks. Uh, it, as it suggests, it's a technology which simulates human brain, and it can solve problems using a linked system. Basically, we feed different inputs, and then there is a um, what we say is transfer function, where due to the play of different inputs, uh, final value is predicted, and we want to minimize the error between the predicted value and the true value by the use of minimization of loss function. So this is how basically ANN or ANN modeling is carried out. In terms of food processing, let's consider a process of drying. We can dry food products, but for, let's say, hot air drying, we can consider some of the factors like temperature, air velocity, uh, product size, and then time. So based on those factors, when we feed all of the information and then carry out and modeling, we can predict the drying rate as well as the change in moisture in the product with time. And for one example, I found that the prediction capability of the AND modeling for drying predictions was even better than conventional modeling as well as heat diffusion modeling. Next, I will talk about the genetic algorithm. As the name suggests, is similar to the evolution process on selection of the um, best or survival of the fittest. So let's consider extrusion process. Extrusion process is passing of the feed material through um, inside a heated barrel, which is fitted with screws. So the screws crush and shear the product, and the product comes out from the a die which is placed at the end of the barrel. So this is usually used for preparation of breakfast cereals. And you can see, if you know that the breakfast cereals, they are kind of puffed. So this puffing is a very important process in case of production of breakfast cereals. And the extrusion parameters play an important role in those puffing of the breakfast cereals. So consider the different factors for extrusion cooking, such as temperature, RPM, additives, or moisture content. And we can change those parameters based on our settings or our experiment to give us um, different combinations of those factors, which are individually called chromosomes, as in biology. And those chromosomes give us different output, which are called individual. And those individuals or the collection of all those individuals give us a population. And we feed those population in the model, and then we want to minimize or we want to select the best or optimized situation or condition which will give us the desired result. Um, for an example, um, in this paper, they used chicken meat, and then uh, they 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 ground it, and that ground meat was mixed with NaCl at different concentration, and then it was extruded at different different nozzle diameters and at different extrusion temperatures, and the result was different. So using genetic algorithm models, they optimize the extrusion process. So from this, the extruded meat looked like this, and they have also used those extruded products for different cooking conditions like steaming and boiling. So this is just a preliminary example of using genetic algorithm. Next is fuzzy logic. As the name suggests, it seems unclear, and it deals with uncertain or imprecise data to yield numerical or meaningful data. So one of the example of fuzzy logic is in sensory evaluation. Sensory evaluation, for those who don't know, it's it's testing of the food products or judging how they are based on their appearance or based on their taste or aroma. So let's say I have a juice sample and uh, I want to do the sensory evaluations. For this, I want to know what is the color of the sorry. For this, I have to consider the parameters like its color, its taste, its aroma, and its mouthfeel. And there could be so many other factors. But all these attributes of the product are fuzzy, which means they can be excellent, can be good, medium, fair, or not satisfactory. And we know that these results are uh, like non-quantitative and or mostly qualitative, which means they are fuzzy, and they can take any value based on their membership function in the as you can see in the diagram below. So in case of normal or classical set, there are only two values, truth or true or false, or 0 or 1. But in case of fuzzy logic, it can take n number of values based on the membership function. So in one research, the researchers have carried out fuzzy logic modeling and used the modeling for sensory evaluation, and they evaluated the different parameters like color, flavor, homogeneity, and taste for a yogurt drink. And they observed that the taste followed by flavor were the most liked or most important parameters for judging the um, quality of the yogurt drink. Now, CFD. CFD is a complex numerical analysis process to solve uh, problems related to fluid flows. Wherever there is fluid flow, the CFD can be an important tool for solving complex problems. And it is very much used in the food processing because food processing, as I already mentioned, is very complex. So let's consider a pipe flow. Water or any other fluid is passing through this tube, and we want to see how the distribution of velocity looks like. So for this, we set the initial conditions and the boundary conditions inside the 3D model of our pipe, and then also set the material properties. And then we solve the Navier-Stokes equation in, let's say, different smaller volumes. We divide the whole geometry of the pipe into smaller control volumes, and then we solve the Navier-Stokes equation. So solving this and feeding into the CFD solver will help us visualize the different parameters for the fluid flow, such as the velocity, pressure distribution. Also, we can know the concentration of different entities uh, inside the flow profile. So, for example, um, I'll be discussing two different results, but for let's say for boiling of eggs. So sorry. So we know that there is different modes of heating eggs or boiling eggs, and we want to ensure that the inside temperature of the eggs reach a particular value so that it is properly cooked. Now, for stationary mode, when the egg was not rotated, the temperature distribution after 300 seconds, the inside temperature was around 40 degrees Celsius. And it is difficult to measure using a normal thermometer. So it is very useful to use CFD in this case. Now, when we do some modification of the heating vessel and introduce some rotation of the eggs, the heat transfer was better, and the inside temperature of the eggs, or the center temperature of the egg, reached to the required temperature within 300 seconds, which was not reached for the stationary eggs. So this kind of analysis is carried out using CFD when we cannot measure the temperature or the concentration of different properties inside the product. This is the simulation for the spray dryer, in which the milk particles come from top and they mix with the hot air. And this contours show the velocity profile of um, the milk as well as air mixture. And we can get to know how the velocity profile or the temperature profile changes with at different point of time. Again, we cannot measure with the thermometers. We can use numerical analysis for this. Now, researchers have augmented AI with CFD to improve the analysis, and they get faster analysis in very short time, as well as accuracy is maintained. This is an example for a stirred tank reactor in which we can do mixing of different ingredients. Let's say we want to ferment a food product. Let's say we want to ferment milk. So this is a stirred tank reactor, and as you can see, using CFD and using AI in CFD, the results were very similar, and we can still get good predictions of the distribution even after in shorter time. Next, I will discuss about plant protein functionality prediction. Sara has beautifully discussed so many approaches in using prediction modeling for predicting the protein digestibility, but we are also trying to see how the protein functionality is modeled. So plant proteins, why plant proteins? Because they can cater to the growing vegan demand, and also they are sustainable. Now, for their applications, we need to consider their functionality, and the protein functionality is a function of the protein structure and their source as well. If you can see, this is the translation process of proteins, and it basically translates the genetic code into the proteins inside the RNA. And this code forms the protein chain, which is basically the chain or sequence of amino acids in the proteins. And due to this capability or different amino acid sequence in a specific protein, they try to configure themselves differently in a different 3D structure. So this is the 3D structure of beta-conglycinin, which is a major soy protein. And when we compare it with the pea protein, we can see that since soy has higher cysteine residues, it forms different kind of structure compared to pea proteins. And due to this capability, it tends to cross-link better and forms better gels. It also shows better functionality, as you can see in the diagrams below. So we in PPIC are collaborating with Microsoft on a project where we want to predict the functionality of plant proteins using machine learning. So we have a huge database of structure function data for different plant proteins, and we want to transform them into prediction models. We know that the 3D structure, as I already mentioned in the previous slide, it can be represented into a 2D surface, and in those 2D surface we can map different properties of proteins like hydrogen bond potential or surface hydrophobicity, and then we can derive useful information out of these. So I showed these two properties because these two properties are very important when we talk about protein functionality. So based on the different structures, we can get different functional relationships or functionality for the proteins, and then we want to make predictive models out of them. And so it will help us in determining which protein is better for which application. Let's say for beverage, we want better solubility, and for meat alternatives, we want a good gelling. So we will be able to know which protein can be used for which function. Some other applications like invention of a 3D printed cookie. So the researchers embedded QR codes by 3D printing, and that code can be read by machine vision, and the code can tell us information about the product, like its manufacturing date, its other information can also be embedded, like which warehouse it is coming from, and maybe sometimes it's freshness if they want to really develop something niche. So what it can do is it can reduce waste generation, and we can minimize the use of labeling or packaging. Secondly, researchers have developed e-nose or electronic nose-based quality prediction system for meats. So in this research, so they have packaged fresh meat, and like they have developed a barcode which changes color due to the change in composition of the gas is in the package when the meat decays. So there is change in the color of the barcode, and this is linked to the smartphone app. So when we point the smartphones on the barcode, it can tell us if the products, if the meat is spoiled or not. So these are some of the applications of machine learning machine learning and AI in food process engineering, but there are a lot of others, and it's a very booming field, and it is growing, and there is so much interest already. And I just summarized the use of AI and ML in food processing in a nutshell. So these are the references that I used, and thank you for listening. If you have further questions, I can be reached on my email.
All right. Hello, everyone. My name is Mara Sharp. I work at Microsoft Research here in Redmond. I work as a data scientist. But prior to that, I received my PhD in computational chemistry. And today I will be talking about marriage of my two interests, AI models for chemistry. Specifically, I'll be talking about two types of models, generative models and transformers. Yeah, so recent advances in artificial intelligence have led to the creation of these huge machine learning models with millions of parameters that are trained on these really, really large data sets. And the real advantage of these models is that they can really understand, they can incorporate a large body of knowledge. And while you may have heard about these in the news quite a bit, about tasks that are focused on things like generating images from text descriptions or generating tweets, that isn't a style of, somebody who's on Twitter that's tweeting. Latest research has also applied these models to chemistry-specific problems. Why would these models be useful for chemistry? Well, just in general, lab time is always very expensive. And if we can increase the likelihood of a drug candidate being successful, increase the likelihood of an artificial sweetener having the properties that we desire, well, that can make our time in the lab much more efficient and productive. So first, I will be talking about transformer models. So the transformer architecture was introduced about 5 years ago and has really taken off since then. So what's the big deal with these transformer models? Well, one of the keys to transformers was that they learn how to capture context around a given input. So for example, to understand a given word in the sentence, it is important to understand the context of the word in the sentence, right? You can't just understand the word itself, like the context around it is really important. So with transformers, this context is called attention, as in, you need to pay attention to the context of the word in the sentence. Paying attention to the context is really important for machine learning tasks such as translation or document summarization. Yeah, and there are a number of different families of these transformers that have come out over the years, including things like GPT, BERT, and Turing. Yeah, and so let's take a look at the breadth of tasks that these types of models can be used for. So first, let's take a look at generating images from a text description. So this specifically comes from the model called DALL-E 2, which has been trained on large amounts of text and images. And you can go ahead and ask it to generate an image for you of an astronaut riding a horse as a pencil drawing. And this is what you'd get from it. And, it's doing a really good job and is really quite impressive. The tasks vary quite greatly about what transformers can do. Next, let's take a look at generating code. This comes from GitHub Copilot, which is based on another transformer model. And you can give it a description of code that you would like it to produce. And here it's like pretty specific about what you want, but it will generate the code that you're actually looking for. So that's sort of transformers in general, but what is, how actually do you go ahead and build a transformer? And specifically for us, we're interested, or at least what I'm interested, what I'm going to be talking about is how do we do this for chemistry specific tasks? Well, so there's a two-stage process for building and training a transformer. First comes the pre-training. You train the model on a very general task for which you have lots of data. So for chemistry, this could be predicting a missing atom in a sequence or predicting general chemical properties of molecules. So this process is typically pretty slow and expensive. It requires large amounts of GPUs and long periods of compute time. And this is the really important part, these pre-trained models can be reused for many different tasks. So once you develop the model that has this good general understanding of chemistry, it can be fine-tuned for specific tasks. So if you're interested in some, let's say, quantum mechanical properties, such as HOMO-LUMO gap, you can fine-tune it to predict that specifically. Or maybe you're interested in drug candidates and you are interested in seeing the toxicity of the specific drug. It could be catalyst activity. And this part only requires a small data set and is comparatively cheap and quick to perform. These models, these transformer models for chemistry are available online for you to go ahead and download. It's not like, the pre-trained models, obviously they're very expensive, but you can really bypass this process by reading the papers, finding these online on model repositories. Specifically, this one that I've pulled up here, ChemBerta, can be found on the website Hugging Face. And you could go ahead and take this model and fine tune it for a specific task. I had mentioned earlier that context or attention is the key, is really the key for transformers performing quite well. And so how does this work in practice? So let's take, for language problems, this is how it would work, right? You take the sentence, I went to the grocery store, and for the word went, we know that we should expect a location to follow later in the sentence. And we know that for the word grocery, this is an adjective describing store, right? And so these words are all related to each other and have high attention. In chemistry, these principles are the same. We want the model to understand how molecules are bonded to each other and how they are arranged in 3D space. So let's take a look at this molecule that I've pulled up, which is, I know the details of chemistry, some people here may be experts in, and some people, may, not really want to be going back to their high school chemistry knowledge. But this is a long chain of carbon atoms, and we have one branch with a bromine atom attached to it. And so let's take a look specifically at this carbon atom that I've highlighted in blue. And so we would like the model to understand that atoms that it is connected to that are near it, and which in this case is the atoms highlighted in green. These atoms altogether should have high attention. They should, that these atoms are, related. Former models work for chemistry. Yeah. Okay. So that's sort of, a general idea about transformers for chemistry, but how do transformers actually perform at chemistry tasks? So let me tell you about Graphformer, which came out of Microsoft Research. It's a transformer. Ooh, my light has turned off in my office. Yeah. Okay. So yeah, talking about Graphformer, a transformer model for chemistry. that was developed at Microsoft Research. It is a transformer model that incorporates molecular graphs in a transformer architecture, and it performs quite well. It won 2 challenges last year in 2021. It placed first in the quantum challenge, the quantum prediction track of Open Graph Benchmark, the large-scale challenge. It also placed first in the Open Catalyst challenge. So, they work quite well. But this is not, the two, Graphomer and Camberta, which I mentioned previously, are not the only transformer models for chemistry. There are a number that have been developed over the past few years, and these are listed. Some of these are listed below. But, it's great to be able to predict specific properties of a given molecule. When it comes to chemistry, a single property is not necessarily all that we're interested in, for a given molecule. For chemistry, the fun often happens when you're mixing multiple things together. When you're doing, it's not just a molecule on its own, it's a molecule happening in a very specific context. That could be, at high temperatures, pressure could be changing, specific concentration. And so how do we go about incorporating these with transformer models? Well, we can do multimodal learning, where we take multiple types of data and build a model that can incorporate the different types. So for example, we can take something like molecular structure, feed it into a transformer model, and combine it with temperature and pressure, combine it with temperature and concentration to predict solubility for a given solute, right? So we have different types of data that we'd like to include, and we can, use transformers to do predictions, with these different types of data. Okay. So I'd like to take the last few minutes of my talk to discuss generative models for chemistry. So what is the purpose of generative models? Well, oftentimes we're looking for ideas of new molecules to test out in the lab, new artificial sweeteners, new drugs, new catalysts, and coming up with the different ideas can often be very difficult. And so how can we use machine learning models to generate candidates that we could then go ahead and test out in the lab? Well, one strategy for generative models in machine learning is called using variational autoencoders, which generate similar candidates to the data set that it has been trained on. In chemistry, though, we can't just generate any random sequence of atoms strung together. We need to actually generate chemically valid structures. And so previous work from MSR has shown how you can constrain a variational autoencoder to generate valid and useful molecules for molecular design. Here on the bottom right, there are a few different examples of molecules that have been generated for given data sets. Finally, I'd like to discuss a way to generate new molecules that have a specific property. So oftentimes, we're not just looking to generate, a sample of molecules, but we really want these molecules to have a specific property. And so this paper that I'd like to show here is called Satya, which demonstrated how you can train a model to do this. First, you train a neural network to predict a specific property given some molecules. So in this case, they trained the model here to predict log p, log of the partition coefficient, which is a measure of solubility. Once this is done, then inverse training is done. You take the the actual value for log p that you're interested in, and the model can generate molecules that are expected to have this particular property. So that's it for me. Thank you all for coming and listening to my talk. I think we have a short break after this, but these are just some ways and tools at Microsoft Research that we are using these new advances in AI and machine learning to solve difficult chemistry problems.
My name is Angels. I am a senior research software engineer at Microsoft Research in Redmond, and I will be giving an introduction to ag-genomics on Azure. So I will be talking first about why we are interested in agricultural genomics. And then I'll move to talk about a key analysis step that is used in many genomics applications, and that's variant calling. Then I'll present how we can run variant calling jobs or any other genomics pipeline for that matter in the cloud. And then I'll give a demo on this as well. And finally, I'll introduce the concept of tertiary analysis. So let's start with why this matters. We have probably heard this many times, and in fact, Sara talked about this a little bit, and this has been in the news this week as well. But this is real, and I think that we need to keep hearing it. The world population is expected to grow to 9 billion by 2050, and feeding it will require a 50% increase in food production, and up to 75% in some cases. This is a massive increase. And there are factors as well, such as climate change and pests and things like that will complicate reaching the goal to increase the food production. So agriculture, and not the classic agriculture as we know it, but an agriculture that uses genomics and bioinformatics and advanced computing resources and such, will be at the core of the solution to address this challenge. And how is that going to be? Well, I'd like to give you some more background on this. The genomes of crops have changed over decades, sometimes centuries, through breeding to make them the way we want to. The classical example here is always corn, right? The cobs were originally very small. You can see here in this picture, right? They are really, really small compared to what we eat now. So we bred them to make them larger to give us more nutrition. And this is in general a good thing, obviously, but breeding has also brought some challenges. The biggest one is diversity. Diversity has actually been reduced, so crops can't adapt to environmental changes as well as their wild relatives used to do and still do, because they've lost genes over time. Not only that, but to put it simply, with a very similar genetic background across everything that is grown, if one plant is susceptible to a disease, then all of them are. One very clear example of this is banana. The Cavendish banana that we all consume is dying to a disease, Fusarium wilt. You can see in here a picture of a field that is infected with Fusarium. This is actually super scary because entire economies in Central America depend on the banana business. Not to mention that their population nutrition also depends on this. There is also a picture here of carrots infecting with Fusarium. It's a different strain, but the disease is also very significant in carrots. Similar examples can be found in animals as well. For example, in fish, there are declining population sizes and loss of genetic diversity in commercial fishes, such as the Pacific Northwest salmon, which is also causing dangerous situations for them. And at the core of the solution to tackle all of this is genomics. We can analyze the genomes of the original wild varieties, see what genes are missing that could give us resistance to some of these diseases or more resilience to drought, for example, and bring back some of those genes. So I would like to look at more closely one way that we could use to reintroduce diversity using genomics and bioinformatics. As I said, we want to cultivate crops and grow livestock that are more resistant to environmental changes, diseases, or simply that are more nutritious, right? So what we need is to identify the right genes that need to be modified. But we are way behind in the gene identification in crops and livestock that are responsible for controlling the agriculturally relevant traits. But at this point, we can integrate genomics and computer science and agriculture to identify the right genes to be modified. So, for example, we can compare the genomes of hundreds or thousands of banana or carrot cultivars and try to identify the genes that are responsible for Fusarium resistance. Then we could modify those genes in the commercial varieties, which are the ones that are susceptible to the disease. And where do we get all of this data from? One way to get this data would be to sequence and analyze gene banks, which are collections where ag species are stored and maintained. And this can lead to super rich genetic information that points to the right genes. So in essence, what I'm trying to say is with there is available data. So with this available data combined with the right bioinformatics analysis, we can help uncovering genetic information to feed the world. So I just told you a bit about the power of genomics to solve real challenges, and now I want to tell you how we can do this. One way to do it is through variant calling. When I was giving you before in the previous slide some examples about how to address this big challenge, variant calling was actually on the background in these solutions. Variant calling is a very recurrent activity performed in genomics. And what is it? With variant calling, we process the genomes of multiple crop cultivars or animals or individuals, and then find differences among them. So here in this table, I have 4 individuals, and we typically compare their genomes against a reference. Here would be the reference genome. So we can refer the differences in each base pair with respect to the reference. Here I'm also showing a phenotype column. A phenotype is any observable or measurable characteristic of a living organism. Phenotypes are actually not considered for variant calling, but I added the information here to show you where this is headed, but I'll get to that later. The output of this step would look like this, where positions in the genome that have differences in the population are saved. And this holds a treasure of information because these differences are really encoding for the differences in the phenotypes of the individuals. But in practice, how can we do this? Which tools exist to run this analysis? Well, the reality is that there are many, many tools that we can choose from to perform variant calling. Lucky for us, the Broad Institute of MIT and Harvard dictates best practices to do some bioinformatics analysis. And of course, this includes variant calling. This means that we can follow these best practices and use the tools that are suggested. In full disclosure, though, these best practices are usually developed for human genomes, but we can borrow a lot of this. So here, what I'm showing is a plain schematic of a variant calling workflow that follows best practices for one sample only. That means one genome at a time. It uses mostly 3 tools, which are BWI, PCARD, and GATK. And the main 2 operations here are alignment of the raw reads to the reference genome, that reference that I was talking about in my previous slide that we used to compare against, and then variant calling with GATK. This gets a bit more complicated if we are processing more than one sample at once, because there are some additions to the pipeline, and it gets a lot more complicated if we are processing also non-human species. But that being said, this diagram, which again doesn't seem so complicated, is actually very computationally intensive. So in practice, how do we run this if it's so intensive? Well, we are definitely seeing a shift for most companies who are going from doing those things, those analyses on-prem, to doing them on the cloud, because they can reduce processing times from months to days sometimes. There is a real explosion of genomics data being generated, roughly quadrupling every year, which is a ton. So as datasets become larger, the shift to the cloud also becomes inevitable. Lucky for us, the Broad Institute has also dictated best practices to run these tools in the cloud, and Microsoft has collaborated with Broad to host the necessary infrastructure on Azure for these best practices. So I want to take a look now at what those Azure tools are. The tool that the Broad Institute has proposed is Cromwell. Cromwell is an open source workflow management system for scientific workflows. It orchestrates the computing tasks needed for genomics analysis and supports running scripts at several scales, from local to the cloud. So as I mentioned, Microsoft collaborated with the Broad Institute to make sure we could support Cromwell in our cloud. So not Cromwell, but Cromwell on Azure, then it's the system that configures all Azure resources needed to run workflows through Cromwell on the Azure cloud. So Cromwell on Azure requires a very simple installation, but after this, after the installation is set up, then a VM host gets set up to run the Cromwell server and uses Azure Batch to spin up virtual machines that run each task in a workflow. So say you want to process 300 or 500 genomes. Well, then Cromwell on Azure is very useful for users that don't know how to properly set up a cloud architecture to run a big task such as this one, because the users don't have to worry about spinning up those virtual machines to run their workflow in parallel. Cromwell on Azure will orchestrate that for the user. So at a very high level, what happens behind the scenes? Well, Cromwell on Azure supports authenticated access via an abstraction layer. that supports Azure AAD and direct access via the Cromwell API. Then the host VM here runs Ubuntu, is the version 18 of Ubuntu, and Docker compose with 4 containers, Cromwell and MySQL test, which is the backend, and trigger service. Then it uses BlobFuse to mount the default storage account as a local file system. Available to all containers in this case. And then the batch account here that is deployed is used by the backend test to spin up the virtual machines that run each task in a workflow. So what about the code? What is it that we are sending into Cromwell? Well, Cromwell workflows can be written using either workflow description language, WDL, or the common workflow language, CWL. Both languages are a way to specify data processing workflows, and they allow to parallelize executions. And they are actually getting fairly popular in the bioinformatics field. And here, I'm just going to focus on WDL for my next samples. So let's take a look at all of this, how it works in practice. I'm going to do a very brief demo on how to run a pipeline for converting sequence data formats on Cromwell and Azure. In this case, I'll be converting FASTQ files to mapped PAM files. This is something that sometimes we need to do to prepare our input files for other workflows, such as the GATK workflow that I just talked about. So this could be what this is, a pre-processing step. I am going to do this on data hosted on a public Azure storage account. And I will be using 3 files, which are the 3 files that we always need to run a workflow on Cromwell and Azure. The first file is a WDL file here, which contains the tasks that we are running. In this study example, I have only one task that is taking one input argument, is a string. It runs some bash command, and then it's not outputting anything, but here you would just run, just write the output that you want to retain. It runs some Docker container, and the workflow is just calling that task. Normally, you would have multiple tasks that you would call in your workflow. The second file is an input JSON file that contains the paths to all the inputs, and that would include also any arguments that you may have. In this case, I have this input argument 1 that we have in here. You will have that value there. And the last file is a trigger JSON file that triggers the execution of the workflow that it points at the 2 previous files. So I'm not going to go through the code, but for anyone interested in the details, you can actually find the code in this GitHub repository that I have in here. And just as a note, I will be using the Azure Storage Explorer to interface with my Azure container. So that's what you are going to be seeing. So I'm going to exit the presentation mode for a few minutes, and I will show you this. Okay. So here we are looking at the storage container that was deployed with my Cromwell and Azure resource. So to start that run, we want to deposit all our inputs, the scripts and the files in the input container. So that's the first thing I'm going to do. So we go to the input container, and I actually already created a folder here. And I deposited the WDL file and the JSON file. So I don't have to do anything, but if I was uploading them, all I would need to do would be to just go to this upload button and just place them here. Our input files could also be uploaded here, but remember, I'm just using files that are in a public Azure storage, so I don't need to re-upload. So the only thing left is to upload the trigger file. So we do that into the workflow container. So we will go here to the workflow container. Oh, by the way, I didn't mention, but when this gets deployed, all of these containers get also deployed by default. So all of this would be here. All right, so now we need to upload the trigger file into this workflows container. And we would do this into the new directory that would be also created for us. So we come here and we upload the file. So let's do that. And that's my trigger file. And that's it. Once this is uploaded, here it is, it triggers the execution of the run. So now, if I refresh, this should disappear because it's going to get moved. But now, so Cromwell and Azure will append an ID to the file name, which is the ID that will be associated to the files that are generated from this run. And then once the run starts, Cromwell and Azure transfers the file from this new directory to the in progress directory. So let's go up, and now there is an in progress directory that was just created, and we should see the file in here with the attached ID. So once this is completed, then Cromwell and Azure will move this file from this directory to the succeeded directory, and then we will be able to find it in there. But this will take a few minutes to run. So what we are going to do is to see one output that I just ran before this call. So also during the run, Cromwell and Azure uses batch account to optimize which VMs are used. So again, we don't have to worry about this. So now let's go into the output folder. And there it is. So here are the 3 outputs that were generated. So we are always going to see this. So the outputs JSON will contain information about the paths of the outputs that are generated. So remember that I was doing a data file conversion. And so what we are looking for is for the output BAM file. So if we open this, now should be able to see it in here. There it is. This will point to where that FASTA file is. So now we could go back to the Storage Explorer and now go into Cromwell executions. And we should be able, that's the ID. And there it is. So that's the output file that we are looking for. So we could just download it and we are done. Just one more comment. If we go back into the outputs directory, there are 2 more files that are being generated. So there is additional information that we can find in the metadata file and in the timing file, which gives us information about the time that each of the tasks took to run. So we can use this to optimize our workflow. So with this, well, you can see that you can parallelize your jobs without actually worrying about the details, and it actually makes it very powerful. So with that, I'll go back to my slides and I'll finish just one more concept. All right, so back to the application now. I want to recap a little bit. I started the presentation talking about how genomics can help with feeding the world population. I said that we can improve our crops and livestock by targeting the right genes. And for that, I show you how we can perform secondary analysis to find where the variants in the genome across the population are. I haven't mentioned before, but the most common type of those variants are called single nucleotide polymorphisms, and that's abbreviated as SNPs. So that's what you have in here. So now in the tertiary analysis, we want to answer, what do we do with those SNPs? Another way to ask is, how can I find which are the relevant SNPs to control the phenotype that we are interested in? And that is precisely the point of the tertiary analysis. We look for associations between the SNPs and the phenotype. So for example, in this toy example with 4 individuals and 5 SNPs, our phenotype is resistance to some disease. 2 of the individuals are susceptible to the disease, and the other 2 are resistant. So there are clearly 2 SNPs here, right, that I highlighted. Of the 5 that could explain the differences in the phenotype, just because they are consistent between the disease and the non-diseased individuals. So of course, this is an oversimplification, because in a study, in a real study, there are tens of thousands of SNPs, and even more than that for humans, and hundreds of individuals. And these SNPs have some degree of confidence associated to them too. So we can see that in this schematic from the National Human Genome Research Institute. So what I'm trying to say here is that in essence, this is just not so simple. So, so in practice, how does this get done? How do we process this large amount of SNPs to find agriculturally desirable traits? Well, genomic data has been traditionally used by plant breeders and animal breeders to perform genomic selection of desirable traits. Mechanistic models can be used for this. They can be very precise, but can't really scale to a medium or to a large number of individuals. So animals and plant breeders, what they have ended up doing over the years has been to adopt statistical methods to select candidates and accelerate these breeding cycles, because this can take a lot of years. However, although statistical methods have really advanced our knowledge over the years, they are very limited because they assume a linear relationship among the features, and we know that that is not true. So this is where AI approaches can really make a difference. AI approaches can overcome this limitation because of their ability to model complex nonlinear interactions, and have really more recently started to receive attention in the genome to phenotype prediction space. And this will be precisely the focus of the next two talks. In these presentations, we will hear from applications of AI and deep learning in different scenarios of tertiary analysis for both the livestock and the crop space, and also from both academia and work that we have done here at MSR. So with that, João Dorea, who is an assistant professor at the University of Wisconsin-Madison, will be next talking about harnessing the power of AI for animal phenotyping. Thank you.
Okay, thank you very much. Thank you, Angel, for the great presentation. Thank you, everyone, for Javier and Angel and everyone here today for attending this presentation. It's a pleasure for me to be here and talk a little bit about our research. So I am assistant professor at the University of Wisconsin-Madison. So I'm affiliated to the Department of Animal and Dairy Science, and also the Department of Biological System Engineering. And my research is centered around the use of AI and sensing technology for animal phenotyping. Okay, that's what I will talk today and show some of the applications that we have in our lab. So Angel made a great point about the use of genomics and DNA intermediate phenotypes to reveal mechanisms and to be used to predict traits that are very relevant for agriculture and for plants and for animals, right? And we have seen the development and how cheap and how accessible this technology related to DNA or to genomics and proteomics are getting and are advancing. But all of these will only be possible to be used and developed if we have phenotypes. So it's clear to me, and I collaborate a lot with geneticists here in my department, that the phenotypes, which are these measurements that we collect at the animal level, they are the bottleneck to advance genetic selection and animal breeding programs, and also they are the limitation for better practice and better management at the farm level too. So that said, the area we are focusing on most now is the use of the technology to predict these phenotypes, and then using these in collaboration with geneticists to put together the phenotypes and the genetics, and then advance the field of livestock, which actually is the area that I work. So, and if phenotype is the bottleneck to advance livestock operations in general and crop as well, what should we do to collect these phenotypes, right? And the only way we can collect large-scale phenotypes is using sensing technology. There is no way we can advance genetics and farm management if we don't have large-scale collection of that type of information, which is going to allow us to develop models that will help with animal welfare, with animal health, to improve productivity of these animals and keep the system as sustainable as possible in the long term. And so using the technology will be key for us to collect these animal lab information. And there are different sensors that we can use to do that. Cameras, drones, microphones, mixed reality and virtual reality and robots, and all of these is available now, and you can leverage to collect what we call complex phenotypes from the genetic standpoint, but at the same way, what we call hard to measure phenotypes, right? So collecting data as animal behavior, infectious disease, body composition, methane emission, this is really difficult in large scale, and especially considering data in the temporal scale. So if you want to collect over years, more longitudinal data, this is also critical and will be really difficult to collect with sensitive technology. So if we think about that, there are two returns that will come from this type of development. One return is related to farm management decision, right? So we develop technology to get animal phenotypes so we can monitor animals better, or we can collect important traits from these animals. And some of these phenotypes will be used in terms of management that automatically generate a return at the farm, economical return. Okay. Some of the phenotypes won't generate a direct or a clear return immediately. Okay, put that aside now and think about genetic selection. Some of the phenotypes that the geneticists are interested and that actually you contribute to advanced genetics will have a delay for that return to be harvested because genetic selection in, for example, dairy cattle, different from poultry or for other species, but in cattle, that genetic selection will take some years to be implemented or for the result to be seen in the field. So that combination of the technology that will advance farm management and the technology that will make genetic progress should somehow be aligned. Otherwise, some of the traits that the geneticist needs won't be able to be collected massively if there is no benefit of collecting these phenotypes. So collecting these phenotypes is a combination of how much this phenotype can help with farm management, and at the same time, in the long term, how much this phenotype will improve the whole system through genetic selection. So today, we're going to be talking about AI, and there are different technologies that could fit on that category. But in my lab specifically, we have a primary interest in computer vision. And I'll try to convince you pretty quick what's driven our attention to start working in this technology. And one of the reasons is that the power of the data is tremendous when you think about imaging data that we're collecting from livestock now. Here is just an illustration of an accelerometer in 3x that we collect from an animal. And the animal is performing two activities here. Okay, that is, you can see the red, green, blue lines. They represent the g-force of the 3x accelerometer. And then graph 1, the animal is performing one behavior. And graph 2 here on the bottom, the animal is performing another behavior. So it's clear to you that there are two different activities. And we can see that in the signal. But unless I tell you that this is grazing, there is no grazing, there is no power in the data. You cannot do anything with the data without that label. But if I give you the label, you only able to predict grazing and non-grazing and nothing more, basically. And unless you have more information about the data of the signal that was collected, you cannot do much. But then when you compare this with a segment of video, it's completely different, the amount of information you can get out of the data, right? So in this case here, you look this video segment and you see this animal grazing, and you can see much more than only grazing. You can count the number of bites, you can count the number of steps, you can see if the grass is green, in the case of the non-grazing, you can see even more. The animal actually is ruminating at that moment. You can see the animal is not standing, the animal is lying down. And that tells us that even with no information, we can capture a lot of knowledge, let's say, from this image, right? Which is different from the signal that we have here from the accelerometer. And then this can go even beyond a primary interest on behavior. And so if you look at this image, you can see cloudy skies, trees, you can actually classify the breed of the animals and count the number of animals and potentially compute the stock density, how many animals per unit of space, and so on. So for that reason, and that's a very simplistic illustration of our interest in image and computer vision. For that reason, we are collecting tons and tons of phenotypes through image analysis and processing these for real-time monitoring and phenotype collection. And we believe that in the long term, the data that we are collecting now will be even more useful as we keep developing more algorithms. For example, these deep generative models that were presented today and other type of algorithms that can render, for example, 2D image and 3D image. And so the power that of the data that we're collecting now will not decrease over time, but potentially will keep increasing. Okay, and thinking about imaging in farms, we can use from RGB image, very simple image that we have in our phones, to depth image that will help us to compute shape of animals, body volume, and biometrics, and thermal infrared thermal image that will give us some thermographic signature or temperature related to the radiation of the object in the scene, in our case, animals. And so there are a lot to be used in the context of livestock. One thing that we always forget, I guess, is that when you think about image in livestock, it's not about thinking in image in the context of healthcare or the industry where connectivity and infrastructure is much more developed and established, right? So in livestock, whenever we start collecting 1 million data points, hundreds of thousands of data points, this is one thing if we are thinking about milk yield, dry matter intake, a scalar, like a single small number that will be transferred from the farm to someone else. When we think about image, we always need to remember that the image is this matrix or matrix of data that need to be transferred. And so when we collect millions of data points and a data point is an image in time, then that's piles a lot of information. And so transferring and processing that information at the farm level, or transfer these from the farm to a cloud or to another place, we require a little bit more thinking, because then it's not that trivial anymore as it was when we were transferring regular data, which will actually still challenge given the challenge that we have in connectivity. But we need to recognize that the advance in deep learning and other algorithms are just unbelievable and became the state of the art to process image. And this could be from a simple image classification to say there is a calf here or not, or to segment animal body, to run classifications based on 3D shape and do object detection, instant segmentation, or even generate a fake image that may help us somehow. Okay, and so today I will present some of our research, and most of this is based on convolutional networks and how we're using them to generate the phenotypes from the image data that we are collecting. So when you think about phenotyping, especially in cattle or pigs, we are very interested at the animal, the individual level. So Angel showed the genome with a disease, and that disease is the phenotype, and that was measured somehow, right? And she mentioned in individual 1, individual 2, individual 3, individual 4, in her table, there was an identification to each individual. And this is key if we want to monitor a large group and have that for any purpose. That could be genetic selection or for management. And so animal identification is the first step in any system that will collect individual phenotype, right? And there are technologies already used, for example, RFID, which is radio frequency identification. It's used, but a lot of research has been developed in terms of using image as a way to identify animals. And this came from a long time ago. So if you look, Journal of Dairy Science, 1922, a research from Minnesota, tried to identify the animal based on the muzzle, the nose pattern, that this is cattle. But that during that time, obviously, they didn't have fancy GPUs, they didn't have fancy algorithms to run classification and so on. So right now, if you go in the literature, you're gonna see recent papers doing animal identification based on the muzzle pattern, but then applying convolutional neural nets and other deep learning algorithms to classify the animal. And then you can go moving from retina, eye image to classify the animal, assuming there is a signature, or features related to the face of the animal body that we would be able to identify these animals in nature individually, identify them. And actually, if we think about cows, which I'll be talking more today, you can actually look to the black and white code color pattern of these animals and use this as a barcode or QR code type of identification system. And then we would identify these animals based on dorsal view. And today I'll be talking a lot about that last option here, and I'll explain the reason. Okay. So we have now a farm, and I think this is a kind of a real example when you think about AI and phenotype collection. We have in the farm, in our research farm here at the university, 500 cows at this farm, and we have 4 exits of the milking parlor. So the cows come to give milk, and every day they return through 4 lanes. You see 1 lane here, another lane right here, and on the other side you have the other 2. So you have 4 lanes, and these lanes are equipped with these very simple depth sensors. We have these 3D cameras or depth cameras that acquire frames of these cows every time the cows are walking through the lane. Okay, and the reason we are not using face detection, eye detection, nose detection, it's because in large scale it's extremely difficult to collect the information to train our models, because the animal interacts with the device. Usually the distribution that you have in a training set go really different from the distribution you collect when the animal has all these possibilities of changing postures and turning around. So it's much more difficult to scale up. And so we found through our research that positioning the camera in the top-down view would give us the best scenario to collect that information. Okay. That being said, this camera has a depth sensor. As I mentioned, is a depth sensor. It can measure the distance from the camera, where the camera is positioned, to the floor, and so keep calculating this. And so whenever this change, because the cow is walking through, this will trigger the camera and acquire a sequence of frames. Okay. Okay. So the question now is, this is large scale. We don't manipulate in terms of hand picking the image. So we want to build a pipeline that would be automatically automated in terms of data collection and analysis. So for that, we have used cloud computing. And one thing we have done is, whenever this sequence of images is collected, we send this to the cloud. And on the cloud, we have a lot of automation steps that would process or pre-process the data before final analysis. So the first thing that happens is when the animal is walking through the lane, you can collect good image and bad image. And so the good image for us will be always the image that will have the entire animal in the image. So the animal is not cropped and the animal is all there. The bad image would be image without animal, the animal is cropped, or the image is blurry, or all problems that you could classify or could characterize in the image. So we train a very simple network that will classify good and bad images. We have only 2 classes, and these help a lot to remove data that is not necessary, and so we don't spend time and money processing things that are not good. So for example, here from 52,000 images, we go down to 19,000 images that we'll consider good in this pool of images that will come sometimes randomly, because we set a sequence, and then the units, the number of images are always the same, but then how many good images may vary. So in that pipeline we are using in the cloud, we have another trigger that says, if the image is good, call a model that is already trained. We have a giant model here based on several type of animals and different ages. There is an image segmenter that will basically segment the animal body. And on the lane is not a very trivial task. We can not apply threshold and things like this, because the animal is very tight. And so we have pixels related to the infrastructure that are very similar to the animal body. Anyhow, we have this trained and performing very well, so we can segment the animal body here. And so if the animal body segmented, then we apply this mask into the infrared image, or we apply this mask into the to the depth image. And now we have in a specific blob, in a specific storage, the images that are good to go for animal identification and the animals that are good to go for body condition score, body biometrics, body weight, whatever decision we would have in terms of processing or phenotype for that image. So that infrastructure, or this pipeline that we built, was very important because it can be implemented in beef and dairy, in pigs, any animal that would have similar management routine. Okay, and so if we think about animal identification, then the first question that probably asking is, okay, how this guy is identifying animals based on the black and white coat color? So that's what we're doing. Animals, we have unique signatures, and we are using this black and white distribution to train the models that will recognize animals based on that unique signature, and so we know the ID of each animal. Okay, and the accuracy to classify these in a group of about 100 animals was about 96% accuracy. So it works very well, even if you have a little larger data set size or number of animals. Now, if we increase and if we go to 1,000 of animals, what's going to happen, and this is a challenge, is the degree of similarity among animals will go up. And so we need to be careful and to see how we're going to process that information, because now we have 5 or 10 or 15 animals that are all black or all brown. And so this is a challenge, and we are trying to address in terms of identification. Other challenges that I won't discuss these a lot today are some of the cameras that we use are cameras off the shelf, and so they are not designed specifically for this application, which can be looked as a challenge, but at the same time is ready to go. We open and we use, and has worked very well for us. But sometimes in farming conditions, we're gonna have issues, for example, related to light condition, right? So, and these may interfere with the camera, and that could be pretty much any of these cameras. And so we need to pay attention how we filter or how we correct for these issues that we have. And so we have all the issues related to environmental effects. So the animal is covered of dirt or covered of snow, and so how we identify the animal based on the color. And lastly, image annotation, how we do this. We're going to do this supervised or not, and how we annotate that data to have good predictions. Okay, so when we think about phenotyping and technology and AI or computer vision implemented in farms, we need to remember that we're implementing these in farms. And so the challenge is it's usually beyond we imagine that would be. Here's just a very quick example about how we are annotating image in a more efficient way. So we are averaging semi-supervised learning, so using a technique called pseudo-labeling. And in our case, where we have image very well controlled, is working very well. So briefly, if you've never heard about this, if you have a small data set and you have one class that is blue and then one class that is orange, and you want to train a model to classify new individuals, but you have a small data set, the performance of a model probably bad. So what you want to do is what we can do to leverage a very large data set, but where we only have few classes annotated or few individuals annotated for each class. So in this case, if you train a model and you apply this to this unknown huge data set, we're going to get predictions that you have a high confidence should be blue, a high confidence should be orange, and some other predictions will have a moderate or low confidence should be blue or orange. So what we do then, we set a threshold to say, okay, those are the predicted blues that I believe, that I trust, and those are the predicted orange that I trust. And then we reincorporate this in the data set and retrain, and then we evaluate in an independent data set, so we see the benefit of using this pseudo-labeling or that we are reassuming as a good predicted value. And so we apply that concept in a data set for animal identification. And here we had initially 233 images only, okay? And when we train a model to classify individual animals, we had an accuracy of 33%, so very bad, okay? So then we start adding, and we went to 500 images or 1,000 images with annotation. and our accuracy went up. The baseline accuracy went to 50% or to 70% accuracy. So that was good, but not good enough. And so what we did, we had unlabeled 20,000 images, and here we have with label only 1,177. So we applied this model with 70% accuracy only on these 20,000 images. And so we harvest from the highest confidence ones, the predicted values, a total of 20,700 images that we now assume as true, and then we retrain the model, which brought us to an accuracy of close to 90%. So we increased 26% in this case here, our accuracy to classify the animal. And so we started initially with 1,000 images and end up with 20,000 images, and we came from 70% accuracy to 9% accuracy using this simple technique. So that was a very efficient way to annotate the data. So obviously, we can combine our technology with other technology, or we want to say our technology with the camera technology, with other technology, and we do that. So we have RFID combined with the camera, so we can label minimally the data in order to get going, and especially under the condition that animals will move around. You have animals in one pen, and this animal will leave the pen and go to another pen, and so the number of class will constantly change. And so we have leveraged not only other technology, but also contrastive learning and other techniques that we identify a new animal in the group. But another question that is very common is, okay, what happened then for the animals that are the breeds that are all brown or they are all black, right? So how are you going to identify them based on the image? So we recently published a study which we investigated the potential of 3D representations for animal identification using 3D deep learning or regular normal 2D convolutional networks. So in this study, we tested voxels as one 3D representation or point clouds as another 3D representation, and we compared that with death image, which somehow is not a 3D representation, but would capture some of the 3D information in the image. And then we found a very good quality in terms of our capacity to identify animals based on the shape. And in this case, this result was using exception and using the death image specifically. And one question that we had was, okay, what happens if the animal is growing? And so the animal is changing shape and changing biometrics, and we don't know if we'll be able to identify animal in the long term, right? And so we had an initial trial that we got calves. These animals are in growing phase, so they're changing body super fast. And we evaluate these animals for 6 weeks, and we start skipping weeks, so training the model with week 1 and 2, and try to identify the animal at week 3, or training the model with week data from week 1 and 2, and try to identify the animal at week 4. So skipping 1 or 2 or 3 weeks between the training set, the image we used to train, and the image that we got to test. And so we have a slightly decrease here from skipping image, but overall, what we noticed was even the animal growing, we were able to identify the animal based on shape with no color information at all. But that was a short term. So what we are doing now, we have image from animals from week 1 of life, and we have the same animal 2 years later. So we want to use this image at this first day of life and try to identify the animals two years down the road. And we are facing some challenge, and we can discuss this more, but there is a lot of potential, but the animal change a lot the way that the black and white and the shape it's organized in the body. And so we need to evaluate how frequent or how often we need to keep adding data in order to classify the animal in the long term well. And this is very important considering animal traceability. This is very critical if we want to advance that area. And so there are 20 or more papers predicting body condition score. We are doing these just based on routine analysis. The accuracy in the literature will go around that 71% to classify if the animal is super skinny or if the animal is very fatty, and so measure the amount of fat deposition in the body surface. And this has an important management is used as a management tool. But what we're gonna do here, since you have this pipeline set, is using the body change shape to identify diseases that are very important from the management and that are also important for genetics. Okay, and so just a quick explanation of the rationale of this trial. When animals, after calving, a cow will lose body weight. Okay, the cow will mobilize body fat naturally to supply production of milk. Okay, like humans. And so what happens is some animals will mobilize too much fat. And so the liver won't be able to handle that amount of fat and the animal will get sick. So what we do then, we usually try to monitor the body condition or the shape of the animal before calving, so we avoid the animal that has a lot of fat, because this would intensify the mobilization after calving. The animal will have a high risk. So here what we have is we have 21, 14, and 7 days before calving, and we have these 3 death images. That's all what we have. And we have 70, about 80, close to 80 cows, 76 hosting cows. And what we want to do is using only these 3 time points and predict a subclinical ketosis, which is not even clinical, which is much more difficult to detect. And we want to predict this during the first 14 days after calving. So look, this is a very difficult task because my last data point comes 7 days before calving. And I want to predict an event that will happen at least 7 days or 8 in terms of interval between my last data point and the event, right? And actually can go up to 21 if the disease happened in the day 14. So it's difficult, and we knew that. We're not assuming that this will work at the first try, but we want to know how much of this image could inform in terms of the shape of the animal and the risk to get a disease after calving. So we used two approaches. One, we got a pre-trained model that we had to classify body condition score. And instead of using the body condition score prediction, we extract the 1,024 features of the exception network and use these as a predictor to classify the disease, assuming that the convolutional network would extract features, important features related to the shape, since that was trained to classify body condition score. And so we add these to 3 biological features, we call it here biological, which is mask size, so basically the size, the number of pixels in the mask of the segmentation, the surface area, which is very correlated with mask size, and the body volume of the animal. So we put together now 1,027 features per image, and we had 100 images per cow per day, and we had 3 time points and 76 cows, so a lot of features, actually more features than we have cows, right? So because of that, we use partial least squares and gradient boosting and try to classify the subclinical ketosis. And so I won't spend time here, but I can explain details how we train it. Basically, we randomly split the training set and testing set, and we repeat this 10 times, and always the hyperparameter was searched using the training set only, and we then compare that with using body condition score as a baseline. So briefly, we found very interesting results. First, we have a F1 score of 0.75 compared to body condition score only from the cameras, improved using the features from the convolutional network. The recall was 0.91%, so this 91% basically tell from the sick cows, we catch 91% of the cows that will get sick. And then we have 35% of misclassification of cows that didn't get sick, and our model said that would get sick. And so that we knew that this would work perfectly. So what we did then, we start adding information about the cow breed, the cow pedigree, the cow, the health record of the cow and other animal, the diet of the cow, metrics and features that are really important that we ignore initially just to see what the potential here would be. And in this case, the false positives are better than false negatives because the cost to treat a cow, it can go up to 200, 300 if the cow get a clinical disease, it can go up to $1,000 per animal, and so we don't really want that to happen. And so it's better to have, if we have a little bias in the model, it should go more towards the false positives. So in this case, we're very happy with the results and very promising, considering we have only 3 time points that we actually don't even consider this as a time series, obviously. So we treat them independently in this analysis. So because of the power that we can get from the shape analysis of these animals, we started using and trying to solve a problem that we have in the industry right now. That is, now we have the possibility of using sex semen in dairy farms, and that means that you can select the females that will replace the cows because now you have the sex semen. But then what's happening is that the producers are using the other cows that you don't have to use another dairy animal, and you're using a beefy animal. So we are producing basically beef animals in dairy farms. And so because of that cross beef and dairy, there is a complaint in the industry about the shape of the ribeye. So animals from dairy, more dairy genetics, we have a ribeye that's more oval, and animals that are more related to the beef, they have a ribeye that is more circular. And so when we adjust these cuts, depending if it is more oval or circular, the weight of these cuts will change. And so there is a lack of uniformity, and consumers will complain. And so what we are trying to do here, it's trying to predict the shape of this ribeye using a live animal, using the 3D image. And for that, we use ultrasound image. We get the image of the ribeye, we compute the circularity, we compute the area of the ribeye, and we collect thousands of images of 3D shape of these animals, and we try to predict that. So the way we did it, we first train a segmenter, a PSPNet, to classify the pixels related to animal bodies, to basically segment the animal. And then we use the feature maps to predict the shape of the ribeye, assuming that the network would learn about the shape of the animal since you're using depth image, and our hypothesis that the information extracted by the neural network would be better than we would visually do with body volume, body length, body area, and so on. And that actually what happened, our predictions using the features extract for the segmenter in the testing set classify ribeye area and circularity extremely well. And then when you compare with body biometrics, body volume, body area, we didn't have a good performance at all. So there are much more information extracted using the convolutional neural network than we were able to biologically, from our knowledge in animal biometrics and body growth, we were able to do. Okay, so that was very nice, and this can apply to other industry, to other problems too, that we could possibly do this to predict some internal tissues or cuts using the live animal with no need to harvest the animal. And so lastly, we have implemented a large trial combining body growth development, memory gland development, and genomic information. So we have this barn with 240 animals, 30 cameras, 30 3D cameras, 30 single board GPUs, and a system controlling all these edge computing, where we want to measure body growth development of these animals. There are several papers from our group and from other groups in the livestock area, in the animal science area, showing how good is the prediction of body weight using 3D cameras, depth cameras, right? So we publish papers with beef cattle, with pigs, and the predictions, as you can see here, they are very good. The problem is, in a situation like that, it's really hard to transfer the amount of image or those depth image every single day in large scale. So what do we want to do here? We are, instead of using the 2D image to predict body weight, we are getting one vector in the horizontal dimension, one vector in the vertical dimension. We are concatenating this. So here you can see the pixel value is related to the height of the animal. So you can see here one dimension concatenated with the other dimension, the vertical and the horizontal. And we are reducing the image from a regular depth image to a vector of 936 pixel values. And we are using an autoencoder to reduce that even more, and only using the bottleneck of the autoencoder to predict body weight. And I'll explain that why. Okay. So briefly, what we did here, we use an autoencoder with 20 features, and that's one-dimensional autoencoder. So we feed that signal to the autoencoder and extract 20 features, and we use these 20 features to predict body weight, and we compare that with the biological features extract from the image, the whole image. Okay, and so they were very similar, but what's more exciting is the size of the data from having one image or to having one vector was huge. So we went from 600 kilobytes to 0.21 kilobytes in terms of data reduction. And these, for farms, this is very important because if you start collecting large scale information, that type of reduction will play a very important role. And I can tell you, because we have these 30 cameras, we don't have good connectivity, and so compressing that information really helps. And possibly if we can compress even to 20 features and only using the decoder component to reconstruct this in the lab, then it would be good too. And in this pen, we are also monitoring feeding behavior. We are very interested on how many times animals come to visit the feed bank, how long time spent. This is very important phenotypes. Also, we are evaluating how frequent should we run inference? Every second, every 2 seconds, every 30 seconds, because some of these phenotypes won't change in a fraction of a second, right? So for example here, we try to predict eating time, and we want to know how many, the total time spent at the feed bank. And so we ran inference every second, every 5, every 10, every 20. We want to know when the models are missing events, and the error of prediction would increase. And so what you can see here, when you went from 20 seconds to 30 seconds, we basically doubled the error of prediction, because now the animal, we are missing events that's happening. And if the frequency, if the interval is too big, we won't see what's happening at the pen. But it definitely can optimize the system a lot, not running inference every second. We are interested in cleaning phenotypes as well. So here we want to look for the feed bank and see what is the mouth motion. We want to compute exactly if the cow is eating or not. If the cow is selecting large particle, if the cow is selecting corn, if the cow is selecting, we want to look to all of these and compute these accelerations and motion features as the total distance travel, acceleration, velocity. And those phenotypes are extremely important, because, for example, eating time has a low heritability, because the cow can be at the bank, not eating, can be just watching the environment. And any sensor would compute this eating. So what we want to do here is like clean and get better phenotypes with this technology. And another example that we are interested in is related to heat stress. And so we are predicting respiration rate using image analysis. Here, very, very simple, very basic, no deep learning at all in this case, getting the pixel intensity and converting this into a friction domain using Fourier transform and counting the peaks. And so we can compute the respiration rate of these animals in a much better way with much simple sensor. Here's the quality of the predicted and observed respiration rates that we have using night vision, infrared cameras during night, or RGB during the day. And my last message here in interest is how we can change from third-person view from this camera's position in the barn to mixed reality. And we are using Microsoft HoloLens to do this, because we believe there are a lot of potential to monitor more activities and get better phenotypes as well in farms. So here's a student using the HoloLens, and he's milking cows, as you can see. So when we saw that image, we realized how different and how much information we gain in this first view camera compared to any other position that we could have in terms of camera in the barn. And so we want to use this to track the activities and possibly help mistakes that would happen on the fly. So in farms, it will be really difficult to use the hand, because the hand is usually use it. So what we are running here, we have an object detector classifying, tracking the procedures like cleaning the teeth, pre-dipping, post-dipping, wiping the teeth. And so we believe that this could be a unique tool to train new employees, fix some mistakes that would happen on fly, track some protocols. In this case, could be a hygiene protocol, and understand better the human and animal interaction that happen. And we know that some employees will do great and have animals that never get sick, and some employees will have animals that once in a while animal is sick. So what happened at that level of human and animal interaction? So we are doing research on that right now. So thank you very much. I'll be glad to answer any questions. Again, it's a great pleasure to collaborate with you. Thank you, Javier and Angel, and I'll be happy to take any question. Thank you. And here's my group, and now we have Instagram and LinkedIn or in Twitter if you want to follow us there. Thanks.
So today I want to talk about a couple of projects that we worked on where we use machine learning techniques to improve crop production. So Angels touched upon how a crop's genetic potential is important for food production. I want to talk a little bit more about the environment that the crops grow in, including the weather and also the soil, and how the farm is managed. So the first part of my talk will consist of talking is about predicting crop yield or other plant phenotypes from multimodality data. The second part of the talk will focus on using causal machine learning techniques to improve soil health. And then we will also discuss how farmers, food companies, and domain experts can use these techniques for guiding their decision-making process. So my first talk will be about deep G2P, which is a multimodality fusion technique for yield estimation. So with the advances in field of genomics, we are now able to perform studies that map the regions in the genome that are responsible for traits that can help crops be more resistant to droughts or higher temperatures, or resistant to diseases, or become more nutritious. We can go one step further, and we can combine the genomics data with other multiomics data and environmental factors. So modeling these data integrations and their interactions using machine learning techniques can improve our phenotypic predictions and also help us discover better and more nutritious crops. So our goal with G2P is to develop a deep learning approach for yield prediction. And here we are trying to understand how the genome interacts with the environment, which is the weather and the soil conditions, and along with the field management practices, which includes things like irrigation, when the field was irrigated. It includes fertilizers, such as when the fertilizer was applied, what kind of fertilizer was applied, how much was applied, and other things like tilling, if the field was tilled or not. And we want to combine these three different data sources to see what is the effect on different on the crop yield or other phenotypes like disease resistance or plant height. A big challenge is when we deal with genomic data is to decide how to represent genomic data. The first challenge that Angel's already touched upon is the volume, but then there's also another challenge which is related to the complex interactions that happen between the different genomic features to produce a phenotype. So we can actually draw a parallel to natural language, where the meaning of a word depends on its context. And Morris touched upon this a little bit, so I'll go over this quickly. Where the meaning of a word depends on the context, which is basically where it is in the sentence and what is around that word. And when you combine the meaning, combine the meaning of all words, then we have the meaning of the sentence. So we can think of a genome or genes or DNA sequences as the vocabulary, or as the words in the sentences. We have context we have the meaning of the gene is defined by the neighborhood of the gene or the sequence, but then we can add additional context to that using weather, soil, and field management factors. And then the meaning of that entire sentence becomes the phenotype becomes the entire meaning of the sentence. So here we would like to use the recent advances in NLP techniques to build neural networks to predict better phenotypes. And one of the great benefits of these approaches is that they allow us to naturally capture complex interactions between genome, environment, and management techniques. So I'd like to provide a high-level overview of our technique. We have these 4 types of features: soil-related features, and this is including the soil chemistry, soil micronutrients, soil physics, and other features that are soil carbon and nitrogen, other features that are available. Field management includes any field management practices like tilling, irrigation, fertilizer application, etc. Weather features includes features such as solar radiation, precipitation, relative humidity, growing degree days, and other things. And these weather features are time series features. And then we also have genome SNP features, which is basically the seed type or the genetic variations. So we process each of these features using using neural networks. For some of them, we use autoencoders. We process the genome module specially a little differently because we want to capture the local context, which for these genetic variations we get from the reference genome, and we also capture the global interactions between the different sequences using attention-based techniques. Then we also have a separate module which captures the genome and the environment interaction. And for this, we use the concept of cross-attention from NLP. And here what we do is for each genomic sequence, we attend over the weather embedding across the different time steps and add to the genomic sequence embedding. And the intuition for doing that is to understand how strongly the weather at each time step interacts with the genome data. And finally, we have our fusion module, which intelligently combines these different modalities, the intramodal and the cross-modal modalities, which are collected at different time resolutions. So we have weather data which is available more frequently than, let's say, like the soil or the field management features. And we fuse them together to predict the phenotype. So we train this model on across different locations and also on different seed types. So that it works well with it predicts well for unseen locations and unseen seed types. Now this deep G2P can be used for, I have two examples here how deep G2P can be used. So the first one is that it can guide domain experts when they want to test different crops to see which seed varieties will work better in certain weather or soil conditions, or which seed variety is resistant to a particular disease. They can use the inference on deep G2P and see the effect of using a particular seed on, let's say, crop yield. The second application is to determine the best management techniques to apply. So the first, an example of this is after planting, we want to decide what is the best time to irrigate based on weather forecast or soil conditions. and another example of this is, for example, when looking at the fertilizer prices, they are rising, and let's say the farmers want to compare what are the best, what is the effect on crop yield if they use different types of fertilizers. So they can get these kinds of insights by using deep G2P. So I want to now switch to the second part of the talk, which deals with causal modeling of soil processes for improved generalization. We did this, started doing this work over the summer, and I think Soumya is in the audience, who played a key role, and she was an intern who worked with us on the project. So I want to talk now about understanding how soil processes interact with each other, and then study how what is the effect on soil carbon. So why are we studying soil carbon? So soil carbon is related to, or it can improve agricultural productivity by improving soil properties such as its water holding capacity. It can also help to increase climate resilience because healthier soils make farms more resilient to things like drought or even heavy rainfall. But the carbon content needs to be managed, and its proper management can have a positive impact in solving many of the environmental problems. So measuring and monitoring soil carbon is therefore very, very essential and important. So what are the challenges that we are faced with here? The first is that changes in soil organic carbon are not only dictated by weather events and management practices, but also by other soil processes such as plant nutrient uptake, the soil organisms that are present in the soil, the texture of the soil, micronutrient content, and also soil disturbance. So this makes soil a very complex living medium. Because of the complex nature of soil science, the exact relationships among the different soil processes are not known, and there is no acceptable universal model for studying soil organic carbon yet. Also, the current models of estimating soil organic carbon are not consistent with the latest advances in soil science, and they do not generalize well to other locations or different soil conditions found globally. So our goal in this piece of work is to develop robust and scalable methods to study soil carbon changes. And we also aim that these methods can be easily generalized to new use cases, such as different fields, biomes, crop growth, and management practices. Our goal is also to identify or learn the causal relationships among the different soil processes. And for this, we are working on a causal ML model that will enable us to learn the cause and effect relationships to enhance our understanding of the soil dynamics. And we will also be able to do soil carbon estimation, and then also in addition to be able to perform whatever analysis to simulate scenarios that affect the different management techniques that the farmers employ, how they affect soil carbon, and then guide farmers to use more sustainable farming practices. So why are we using causal ML for soil carbon modeling? So here I want to show, I have an image of soil carbon distribution, and this is this data is taken for farms from the North Wike farm platform from Rothamsted Research UK, and they are also our collaborators in this project, and they've been working alongside us on this. So here I have 3 different types of treatments that were applied to the farms. So either they received the red, blue, or the green treatment. The red treatment was where high sugar grasses were sown. The blue treatment was where the high sugar grass with white clover mix was sown to reduce dependence on nitrogen-based fertilizers. And then the green green fields were just permanent pastures. So we see here that with the different types of land uses, the soil carbon distribution is very different, and this is one because of the land uses a difference in land uses, but then also because of the different management practices that were used. For example, the red and blue fields were tilled, and the green field was not. And this is just data from one farm from the same locations. When we try to expand to other geographies, these differences in distributions will become more pronounced as we move to other soil types, soil texture. These differences will become larger. So when we test on unseen out of distribution data, ML approaches do not work well, and especially when when the training data is constrained, because the same learned parameters do not apply anymore. On the other hand, we get better results from causal approaches because they generalize better, as they are able to guide the models towards the true underlying real-world process. So here is our approach. We call it knowledge guided representation learning, and the idea here is to learn from two heterogeneous sources of data, and where we hope that sharing information. So we have here simulated data and real data, and we hope that sharing this information between simulated and real data will help enrich our understanding of the soil processes. So while simulated data offers insight about the underlying causality of the simulator, and we know that these simulators typically need to be calibrated for new regions, we can provide better region-specific insights by adding observed data. Our causal graphs, causal graphs are basically the graphs that show the relationships between the entities that we are interested in, and these could be different soil properties like pH, carbon, nitrogen, or different farm management practices. So we are able to, with some of our experiments, we are able to discover well-known links, and we notice that there is a strong association between total carbon and nitrogen in the soil, and these are related to soil organic matter. And these relationships that we discovered are consistent with theory and other research studies that have been done. And we also were able to automatically discover that tilling changes the pH of the soil, which affects the soil organic carbon, total carbon, and nitrogen. So and finally, the micronutrients iron, zinc, and manganese, they affect total carbon, and which could be due to which suggests that there may be a relationship between the manure added to soils and these micronutrients. So in summary, causal graphs are able to they show us the mechanisms through which the different farm management practices or these different soil properties are affecting soil carbon or are affecting other processes. So one of the important applications of this piece of work is to provide farmers or food companies insight about their farms given local conditions. So we can predict accurately soil organic carbon, but then we can also connect the different farm level management practices to a given a food company sustainability goals to help reduce the agriculture's carbon footprint. And I want to add a little bit about the privacy concerns here, because in my previous talk and in this talk we have a lot we are getting, or we are fusing data from a lot from a lot of different modalities, and these data could come from different sources, and therefore there may be privacy constraints involved. And Satya's talk, the first talk today, showed that that we have like cutting edge technology available at Microsoft, and so it's easy to obtain, or it's possible to obtain these confidentiality and sandboxes guarantees when we run inference on models, and and the user will only be able to see the results and not the actual data. And finally, as in the future, we are going to extend this analysis to other regions and scale our data collection by using other modalities such as satellite imagery. So that's all I have. Thank you. And the next talk will be by Yuan, who will talk about trustworthy supply chains using DNA tags.
And thanks for everyone who stayed late to the talk till now. So my name is Yuan Chen. I'm a senior researcher at Microsoft Research. I have been doing various research using sort of DNA and DNA nanotechnology. And in this talk, I will talk about how we can use DNA tags to make supply chain more trustworthy. So as many of today's talk talking about the food and all kinds of supply chain, they have possible issues in terms of like tracking and tracing. And besides many improvement and innovation in the IoT space, one of the problem in the supply chain really also comes to the limitation of conventional tags. So the first problem goes to physical sort of integration of your tags to the physical object. For example, using food as an example, typically the current tags are unable to label items that are too small or too flexible. For example, if you have cherries or like cheese, or even like liquid-based stuff like wine, conventional tags cannot really label this type of stuff. And the second problem is a lot of these items, they are really in a large quantity. So using conventional tags, it's very cumbersome to label them individually. Also, there's another problem in terms of they are relatively easy to lose. So that would also cause your tracking and tracing problem during the supply chain. And the final problem goes to the security part. So most of the conventional tags have a problem of they're relatively easy to forge. So that make a large sort of counterfeiting sort of market to a lot of products circulating in the supply chain. For example, like wines has a huge fake wine market circulating in the world. For example, in China, there's a very large portion of like fake wine. So this is also a big problem, goes to the tax. So here we will talk about how we can use DNA tags to improve all this like tracing and traceability of supply chain. So I will use an example from the farmer to make some kind of produce to do this. So in this example, a farmer would have some information about that fresh produce. Let's say you have an apple, you have the object's name, you have where the farm goes from, what kind of growing condition, the nutritions, all kind of information. They can register all of them to the cloud. And we will be able to encode an ID or to DNA, and DNA, because it's a nanoscale material, they are actually very easy to dissolve in sort of water-based the solution. So you can just use this kind of water spray to put onto your anything you want to label. That will make it the deployment really easy. Once this step is done, now the ID is directly labeled to the object, so they can just transport through the whole supply chain, eventually go to the retailer. And when a retailer or a consumer wants to read a DNA tag, here we also engineer a relatively easy method to read it. It's kind of similar to when you do a quick COVID test. So what's done here, we basically can just swap a little bit of DNA out of the object surface, and we engineer this DNA reading paper ticket by mixing the DNA together with this ticket with some buffer, sitting there for tens of minutes. The DNA tag will be able to trigger a unique pattern, and then this becomes a tag. Then we can use our phone app to read this tag back, to decode the information, and then tell you what's the object's information and whether it's authentic or not. So what DNA tags really brings to some unique features to the supply chain application goes to, first of all, it's much easier to deploy them. Like we talk about, they are relatively easy to integrate or apply to object. And also we have a relatively easy sort of process to read compared to other sort of traditional sort of sequencing DNA typically requires very complicated equipment, and operation here is relatively easy. Just mix your DNA with this reading paper. And we also make the reading process much less expensive. Like we engineer here, we have like a relatively cheap DNA reading paper. So it's also, again, much cheaper than doing like traditional sequencing or some kind of other expensive lab measurement. And finally, we also have this DNA tags. We have some unique DNA encoding to encode some of the information even to the DNA structure to make them really hard to counterfeit them. So here's a prototype of our system. So we can see we have a DNA tags. They are like a solution base in this test tube, and we also have this paper ticket. They are like a quarter size that's used to read DNA. And here we put a petri dish, but it's really like just a plastic container to like sit your reaction happen in that space. And eventually, after the ticket being triggered to a specific pattern, we sit them into this, we call it an ag reader. What it really does is just, it shines the lines from the back of the instrument, and there are some filters to filter out some specific wavelength of the lights so that you can read your DNA ticket and eventually use just a standard smartphone with our app, then you will be able to decode your DNA tag. So here I would dive down a little bit on how we write and read DNA. So when we write a DNA tag, really what it goes starting from like a digital binary tag. So there are some binary bit information. And the first step we do is we encode with an error correction codes. So the error correction codes will be able to help handle some errors occurred in the molecular process later. And after that, we do this sort of DNA encoding. So really it's converting from the digital bits to DNA molecules. They are sort of in a separated DNA strands, and eventually you mix them to create a sort of a mixture that's your DNA tag. And then this can goes to your object. So when you want to read a DNA tag, like we mentioned previously, basically you will swap your DNA, put it into like a solution, and then this will be able to interact with your DNA reading paper to generate a unique pattern. And we have a camera, so we can use our own developed image processing pipeline to read the DNA tag from an image pattern to a binary code. And then finally going through a decoder process, we have to get your binary barcode back. That's how sort of DNA's read and write is being done. So here I will show you a demo of how sort of DNA tags is being done. So what we are doing. So here's an example. You will start from take an image of the paper ticket before you put a tag on. So you will see what it looks like initially. So you can see there's a tag there, and here we pipetted a little bit DNA tag solution to the surface of this plastic container. And now basically we just need to put the DNA paper ticket to sit on top of the solution, let them interact. And then just sit it for like 20 minutes or so. Now we will use some buffer to wash the ticket. And now we basically just need to dry the ticket. It's basically using air to blow it. After drying, then we just need to put on the imager. Now you can see there's a unique pattern. And by taking an image, upload it to our app, we'll be able to decode the barcode back to you. Yeah, so in the end, I also want to thank our collaborators from UW. There are 2 postdocs, Jiang Li and Anuja Shiro. They did all these amazing experiments to help develop this DNA tag project for helping the supply chain. I also want to thank all the audience attention. And please feel free to drop me any questions. Now I will hand the talk to our final speaker, Ranveer, to close the session. Thanks, everyone.
Yeah, thank you, Yuan. And thank you to everyone who's attended and stayed for this long. We'll continue this tomorrow. So today what you heard was more about the work we are doing to help researchers advance the state of the art in using tech for food. And I wanted to give a backdrop of the work that we are doing here at Microsoft, and you heard some of that. We sampled some of the work that we presented to you today. It was mostly on research that we are doing in this space on various aspects. Jiang talked about some of the AI capabilities. Satya talked about how you can enable a data sharing pipeline across the different entities in the food supply chain, to genomics, to using causal ML, to chemistry. You heard a lot of the latest tech that we are building. As we are doing this, we would love to partner with you. So if you see opportunities to use some of the tools that we are doing, or to partner with respect to the data that you might have, you want to co-author work, you want to use some of the tools, please do reach out. We'd love to work with you as we define all of these capabilities for the future of food. Tomorrow, what you're going to hear is a lot of the tools that we are making available. So think of it like a tutorial on farmvibes.ai, this thing that we had open sourced recently, and we'll teach you on how to use it. And that, again, we expect it to be a conversation where we would love to hear from you on capabilities that you would want us to build and to release for that. So to conclude, for when we think of the future of food, we believe it is going to be more and more data-driven. A lot of our initial work with FarmBeats was on digital agriculture. What we have been looking at that is beyond that throughout the entire supply chain, on the farm side on sustainability. How do you carry information through the supply chain from farm to food production all the way to the consumer? And then the third part is on how do you produce food itself? And throughout the entire supply chain, we are bringing data and AI and making the entire process smarter and more transparent, which we believe if we can unlock this, we'll be able to grow more food and more nutritious food to feed the planet. And we are not the agriculture or food experts. What we can do is bring the latest, the most cutting edge in technology to the food industry. And the way we can take it forward is through the partnerships that we are doing with you. So thank you again. Really excited about everything we heard today. Please do reach out to us, to the presenters, and look forward to seeing many of you tomorrow as well. Thank you. Bye.